Good morning. Today we are going to talk about cryptographic algorithms and their various implementation and mitigation techniques. So, I pretty much tried to not get into mathematics, just stay in the very higher level of abstraction to cater two types of people. If you are trying to implement, where would you start? And if you already have an implementation working in industry, you want to integrate into their system, where would you start? So, it is from both perspective, developer and as well as designer. Once we talk about these algorithms or at least give you an overview, your objective would be two things: to understand what does these algorithms actually achieve, how do they achieve it, why there are so many algorithms, which one is better than whom in terms of the security strength and hardware overhead. If I have an objective function, if I am trying to design a system, which one do I implement and why, and also some idea about what are their security strengths, what kind of mitigations can we do, all that stuff. So, it is a laundry list of items. Initially it may seem scary to you, but as I said, I am going to go through very simple thoughts, very high level idea of what they do. So, before we start, let us start with the usage model. On your laptop, you are trying to do a banking transaction. You opened an HTTPS, or you have on your phone, you have the app, secure app, and when you basically try to talk to your bank or connect to the bank server, secure server, it is basically uses transport layer security. In fact, most of the cryptographic algorithm that I am going to talk about is basically what this today's transport layer security uses, and I am just listing them. Right now it may seem like too much scary, but eventually I will zoom into each of them. And so, whether it is an encryption algorithm, what is the key size, what is the mode, what is the hashing or authentication mechanism. So, that is basically what I am going to talk about. So, you get an idea, that is the first thing you will understand, what is getting used and what they are actually at the right at the bottom bits and pieces. And then most secure or root of trust is actually the processor in your design. Processor, in fact, the processor which uses some secure socket layer, one of the implementation it runs, you will get an idea of that too. But more importantly, even the processor itself is not secure, or the whole environment, to make sure there is something called security engine. So, I am going to talk about that security engine. Most commercial products that you buy, whether your phone, whether laptop, whether TV, in addition to all the chipsets you hear about, you mostly do not hear about this node called security engine. So, I am going to talk about that security engine, but of course, security engine by itself is not useful, it takes help from all these cryptographic modules. So, that is basically the power and how that security engine works. So, and that is basically I am going to zoom in. That security engine may include processor may be outside, or the security engine may have a processor on its own, which is not the general purpose processor that is used for doing your HTTPS and secure socket layer and all that. It may have all the stuff, but today I am going to zoom into the cryptographic components and how do they talk. Is it inside the security engine, is it outside, how do they help each other. So, today I am going to basically zoom into this component. So, anybody has any question on the context? You are trying to do any secure communication through VPN, SSH, SFTP, HTTPS, anything you do, the root of trust these days in the system on chip domain is controlled by something called security engine. Now, you might say, well, wait a minute, did not we talk before about trusted execution environment, security enclave and all that stuff? How does that relate to it? It relates in the sense this security engine is giving you this same level of opportunity. Your trusted execution environment could be implemented on it, it could be orthogonal to it. Now, before I go further, we want to again reset our context, what we are trying to achieve and why. And this all boils down to same thing, a notion of a sender and a receiver and in cryptographic community they are known as Alice and Bob, and it is all about passing a message, and assumption is this area is trustworthy, this area is trustworthy, and as you go along we will also break that notion, and communication is something potentially untrusted. So, therefore, when I am sending the message, my expectation are at least these three things. Authentication, when a message comes from S and the recipient is looking at it, it should be from S, it should not be from anybody pretending as S. So, that is the authentication, and then privacy, when the S and R talking, nobody should be listening to this conversation and understanding. So, this should not be allowed, that is basically the privacy issue, and the integrity issue is if I am not able to hear, can I actually alter whatever the message is, can I alter the message before it goes to R prime, that is the integrity issue. And different cryptographic components are designed to address these things, and today we are going to zoom in. For example, data integrity could be SHA, it could be parity code, it could be checksum MD5. Actually, the initial version of SHA was built on top of MD5 and then eventually that got broken. Now, the SHA-2, essentially SHA-2 is used today. SHA-2 and SHA-3, those are used in today's protocol. The TLS uses SHA-2, and that is what I am going to zoom in. And then for authentication, you basically want somebody to sign, like the way people sign the check, somebody's signature. So, this is basically authentication mechanism, and for privacy you need some form of encryption. It could be AES, RSA, ECIS, and we will zoom into some of those components, but I wanted to put them in the perspective, so that when I talk about each of these module, it should not appear to you some bunch of random stuff. They have their clear objective, but some point later it may seem blur, because many of the encryption techniques actually is authenticated encryption. In fact, RSA, although it is an encryption technique, you can also use for some form of authentication and signature mechanism. So, there are bound, in fact, this ECDSA and ECIAS comes from elliptic curve cryptography. One is primarily for encryption, another is primarily for authentication, but whichever it is, and even things get even worse, many of these techniques like ECDSA actually makes use of SHA as in the back end hashing mechanism. So, what I am going to do after this context is clear, I am going to zoom into each of them and very conceptually look at what they try to achieve, what are the challenges and how can we solve some of the challenges, and that would also tell you what are the vulnerabilities, because all the guarantees that are given to you are by these cryptographic modules, and if they fail, then everything you build on top of it, which is security engine, on top of it you have transport layer security, everything fails. And that is why this is known as hardware root of trust, and that root of trust relies on the guarantees of this module at the absolute bottom layer. Always we had this feeling, or unless you learn cryptography, you will always have the feeling the hardware root of trust is basically based on CPU, which is partially true, because as I go along I will talk about RISC-V based cryptographic extensions, which is a software kind of pseudo software based implementation of security. So, this is true, you can run each of these modules in software, in fact in TLS that is what it is, or you can speed them up as a hardware implementation, and that is when you hear cryptographic accelerator. It is actually not an acceleration that we discussed in this class, not GPU based, not TPU based, not FPGA based, it only means same cryptographic module implemented as a hardware. Any question? Cryptographic accelerator is nothing but hardware implementation of all the algorithms we talk about, and if people do not talk about acceleration, then it basically means the software functions you are calling, or somebody is calling. Who is that somebody? CPU is somebody. So, therefore, calling CPU as root of trust is actually not a flawed assumption. but for majority of the cases CPU does not participate any of these activities. Directly security engine with its own controller call this, let us say it has its own cryptographic modules, AES module, and I will show you exact framework of that. Any questions on this? Now, authentication, you know what we are trying to achieve, that is what we will achieve using some form of PCDSA, and little bit of introduction of encryption before we zoom into how AES achieves it, how RSA does it, because our objective is we believe the sender, this is a plain text message, this part is secure. We believe receiver, again plain text message, this is secure, but the message need to be encrypted, this is ciphertext. So, basically one of the mechanism is you encrypt it. So, encryption, you give the plain text, whatever message you want to, if you do not like the word P, change it to the message M, and then you need a key, and then it produces the ciphertext. Now, for decryption you give the ciphertext and you get back the your original message, that is the key idea. Now, we talked about earlier there are two types of, and we will have examples of both today. Symmetric crypto systems, when the keys are exactly same key it operates with, and then we will have asymmetric crypto systems where keys are different, and these also have different variations, but typically this one is easier except the key distribution problem, because you have same key. This one is easier in the sense when a sender and receiver is there, then when sender sends to the receiver, it basically encrypts with the public key of the receiver's public key, and the way algorithm is designed that when the receiver receives it, this ciphertext, it basically uses its own private key, okay, public, let us call it PL, it uses its it decrypts this particular message ciphertext using its own private key, let us call it PR, and private key nobody knows. Now, the beauty is sender is not sending to just one recipient, sender is sending to maybe multiple of people, and everybody has their private key, sender is not aware of it, but sender is aware of everybody's public key, that is why the name public key, and same argument applies, the receiver one also knows the public key of sender. So, during encryption process you basically use the public key of whom you are sending the message and use that public key to encrypt, and the way algorithm is decryption time everybody uses their private key to open it, and key sharing problem is solved. Public key is a known thing, you can just put it anywhere and everybody knows. Now, during authentication process it is actually inverse of the problem. When you are trying to do authentication or sign, you sign using your private key. The way algorithm works, everybody when they receive, they be able to figure it out using your public key. So, R would be able to figure out using your public key. So, that is basically the swap of the story. But either way, each of these has pros and cons, and sometimes even if key is not equal, many algorithms, as you will see, one key can be derived from the other, and I know that has some technical flaw, but you would see soon. Any question on the basic idea of why we are doing encryption? Because we do not rely on this communication, we believe somebody will steal it, we believe the privacy is in danger, that is why you want to encrypt, nobody can listen. So, threat model is this part or this part of the communication is not trustworthy. So, this part is not trustworthy. So, that is the threat model. In that threat model we are doing encryption to make it secure, and then encryption we have two choices. Do we have same key for everybody? Encryption, decryption, sign, verify, everything is same, and here you have different, and signing verification process the key usage and encryption process key usage is exactly opposite. These are very basic concepts. Now, let us get into the first one, AES. AES is a symmetric key encryption algorithm, later we will come to asymmetric key. like elliptic curve cryptography is a asymmetric key, public and private. It is a symmetric key algorithm, and Dr. Karfa talks in detail. So, I will give a perspective from a different way about this algorithm. So, this one is adopted by National Institute of Standards and Technology in 2001. It operates on 120 bit block sizes. If you have an email you want to send, whatever the text it is, it would be broken into 128 bits, and then you will be encrypting those 120 bits, and because you are breaking it 120, this is also known as a classical block cipher. You are operating block by block. So, from a cryptographic point of view, block ciphers are not really very strong encryption algorithm. That is why DES or the predecessor of AES, those were broken in no time, and that is why nobody uses them. So, AES is still strong, and in fact, AES or with certain key sizes, AES 256 is exactly what is used in transport layer security, that the one that is used in your banking transaction. So, this particular one is used today. Now, from a layman's perspective, if you want to break this one, of course, it is lot more complicated than that. In a brute force, how many try do we have to do?
2 to the power 128.
How come? How did you get the magic number 128? This one, just the one I circled. I am trying to ask you, what is the brute force? How many try I have to do to break? So, what am I trying to break? I got a cipher text. I want to figure out what is the original message. How many times I have to try?
Okay, from a layman's perspective, I think there are 256 bits key. Okay, so in according to brute force, and if we use Grover's algorithm in our classical computer.
Okay, that is the answer, 2 to the power 256, because in any algorithm in security domain, assumption is you know everything except the key. Only thing you do not know is the key, and it has 256 bits. And so, then if you try all 2 to the power 56 combinations, then one of them has to be the key, there is no other way. So, this is the brute force, and if you look at this number, it is not doable in any meaningful time. So, therefore, but when if you recall the way Dr. Karfa talked about side channel attack, you can use some other mechanism where you do not need that much of time or resources. You utilize some other feature. I will talk about some of those features, then I talk about some of the mitigations. Any questions on this one, that when you look at any algorithm, if somebody says what is the strength, without getting into the details, no other information available, then the strength is 2 to the power of the key size, because key is the only thing not known to you. At least for AES that is true. Once we go along, there will be little deviations. Now, in addition to supporting different key sizes, AES also supports different mode. I will zoom into little bit of that. So, one is counter mode, and which is simply it is the easiest one. Then the Galois counter mode, and finally, the it is a big name XEX tweakable block cipher with cipher text stealing. XEX stands for XOR encrypt XOR, XOR encrypt XOR. But whatever the big name is, AES XTS, I do not know, a lot of people use that one. Most people rely on the transport layer security uses AES GCM. Any question on this algorithm before we go in? And as you see in the picture, it is kind of you have lot of data, you are kind of shifting bunch of row, mixing some stuff, adding round key, you are basically making it complicated for somebody to just reverse those processes or figure that out. And many of those are based on the key, that is why unless you know the key, you will not be able to do it. Any questions on this basic idea? And one more thing I wanted to highlight. So, the idea is not, so the complexity of these, although I lament I am simplified this, but actually each of them are lot more complicated, because if you look at the even the number of rounds is different for the different key sizes. So, it is not like it is exactly same thing. So, for example, what would have been exactly same if message is coming in and you are doing XOR with the key, and if the key size could be 128, it could be 190, it could be 192, or it could be 256, then it would be simple this one. But as you realize its algorithm is actually different, the complexity is actually lot more different. So, now let me kind of get a little bit of perspective what AES trying to do, or what is this picture trying to do, this particular picture. And I am not going to get into any complexity analysis here, but basically it has a initial round, then multiple round and the final round. Final in initial round is just a round key and all that stuff, instead of going through boring stuff. Basically the subcomponents of each of those is basically some kind of sub bytes. Sub bytes is basically you are moving a specific location value from one table to another table. It could be you are shifting some rows. So, these numbers are getting shifted, this value comes to the left and so on and so forth, you are shifting them, or you are mixing some columns with other columns, or you are adding the rounding key and all that stuff that happens. And if you recall how Dr. Karfa talked about it, during these steps there are methods in the madness. By observing what computations are happening in S box, or what kind of round, what kind of pattern you are looking in your digital signature, you could try to figure out based on elimination or small brute force, was this location 0, was this location 1 and stuff like that. You can go from top down, bottom up, you are basically breaking down these sub problems or sub function and trying to figure out, and then you slowly percolate up or percolate down until you find the key. That is basically your objective. So, here is if you are going to implement, now this is, so if you go to open source, try to look for any cryptographic ones. First thing you are going to find is AES. Of course, you will find DES and the other ones nobody uses, you will find AES. You are not going to find, you are going to find AES, at least the encryption algorithm, decryption you may not find, and elliptic curve you are not going to find, and many others I am talk about you won't find, that is one thing. Second thing is, unlike this bus PCI and all these bus configuration which is standardized, for some unknown reason these are not standardized. Every company, and I will explain why that is the case, every company whenever they sell a security engine solution, they have their own kind of boundaries. So, I will show you at least two scenarios, so that you kind of appreciate why people do that. So, but when you are implementing, this is could be one possible implementation, clock, reset and start. So, start is important, because recall this is going to be part of, let me do little bit of security engine. So, security engine is again a piece of hardware that is going to sit somewhere on a bus, and that bus has to be not the bus where everybody else is sitting. This is one of the reliable, it could be AMBA AXB, it is typically not PCI, but this could be a PCI bus. On that bus this cryptographic module would be hanging from there, AES would be hanging from there, AES counter mode. So, therefore, it is important for security engine, if it wants to encrypt a message, and processor sends that request, by the way, that could be through another PCI bus. There are variations of PCI. So, this is where security engine is sitting, this is where CPU is sitting, and it send a request, and why processor is sending that request, because in your original program you have that encryption call, right. Who made that encryption call? In transport layer security, that application has that encryption of your ID, social security number, whatever it is, that came as a request as an instruction here. That instruction got request as a translation to security engine. Security engine in turn send that request. So, that think about your Aadhaar card ID or PAN number, whatever is secure, that is basically flying through, that is flying through from the original application of transport layer security to the CPU, to the security engine and to the AES, and then result would go back exactly the same way. Now, that is why this start is important, because hardware design, by design they are always working, they are always computing something. That is why start and done, these two are important, and no spec will tell you this. You go to any documentation, they will not, but this is important, because when would security engine read the value and forward it to the CPU. Now, you could have done this through some synchronous mechanism, if you know it takes 32 clock cycle. Later I will explain you why that can't be done, or it is harder when many people are hanging. As I go along, you will realize slowly. I will build exactly on top of this how. So, some of these actually I will not take the name which company. So, some of the big semiconductor design automation companies like Synopsys, Cadence, Mentor Graphics, which is part of Siemens, when they sell the solutions, in their internal documentation they will provide exact details what they are supporting. So, that if you planning to add one more module, you are aware of what is there and what would be a problem. Go ahead please.
So one query is like in this diagram, like you have shown with the PCI bus, we have a connected AES module. So is that a hardware implementation such as an ASIC or something?
This is hardware implementation. Very interesting question. This is hardware implementation. Software counterpart would be CPU itself is running. You do not need any more of any of this stuff. In fact, many times many companies when they sell security engine and nobody want to take a risk of trusted execution environment protecting you, they actually rely on the processor inside the security engine, and that processor will run that function, and that memory is sitting somewhere here. That security engine memory, which will have your software binary for AES. So, this is a processor coprocessor model. In this example, you raise a very interesting question. In this example, CPU does not know how to handle any encryption decryption function. Anytime that instruction comes in, it forwards it to security engine. Whether security engine does through a hardware accelerator or through a software function call, it does not matter. Eventually, it will get the result. And so, in a hardware module, even software module, same thing you can do. Start and done is important. Now, clock and reset, I do not need to mention those. Mode is of course important, that is the counter mode, which is in this particular example it would be set to counter. And then cipher key, this is basically this cipher key and this cipher key is same, and block in, this block in and this block in is the same. You might see why is it coming twice, you will see when Galois mode. It is once used for authentication, Galois authentication, once used for encryption. Nonetheless, so this is basically the one only thing. So, counter range, because it is a counter mode, initially it is 0, you can put it any value, does not matter, but what is important, this one is important. Anybody knows what is this nonsense?
Norms I think are random number.
Nonce is a random number with a unique property. What is that property? Never used it again. So, I will talk about, when I talk about random number generator, I will talk about random number is actually not random. So, that is why there is a distinction between true random number generator and pseudo random generator. But nonce basically property, if you reuse it for any reason, even if random number, then replay attack will be able to break it. Any questions on this basic idea of? So, AES encryption, what it does, I briefly talked about this sub bytes and round keys. So, I am not going to get into this, but from a designer perspective, you have to pay attention to these issues. You cannot just say, oh, I have a wonderful AES implementation, I ran it, but how come you are able to break? Because you gave a nonce that's got repeated more than once. You did not guarantee that, you did not check that. That is something, a property you want to check. Same thing for other stuff, counter, block in, and you probably did not do start right, you took the value before the done is true, and all of those issues. Now, one simple thing I want to ask you is that cryptographic algorithms are mathematically secure, then how come people are able to break it? I want to hear your thoughts on this. All the mathematical algorithms, including the pathetic ones like DES that was broken long time ago, they are mathematically secure, guaranteed to be not broken by people unless you try the 2 to the power 256, which is like lifetime of the universe. Why is it we always talk about breaking things like AES 128, I do not think anybody uses anymore. How come? 2 to the power 120 is still a large number. Yes, please.
Because mathematically we are generally checking brute force method mathematically whether it is possible or not, but like Professor Karfa told us that there are other methods such as the side channel method of cracking the AES.
Let us say side channel method is not possible, let us say Paul Cocker did not invent it, then do you believe it is mathematically secure, or do you believe it is secure? Yes.
Maybe with the help of quantum computer.
Quantum computer did not come into existence, do you still believe it is secure? You are on the right track. When mathematically somebody guarantees something, those variables are unbounded, but when you implement it, depending on the machine you are implementing, you are cutting many corners. When you say somebody integer, you are suddenly saying 32-bit, but the mathematician who guaranteed it and proved it, that did not have a bound of 32 or 64 or 128. So, basically those, the way you write if statement, everything has its own issues, and that creates all these covert channels and side channel vulnerabilities. Whether side channel was invented or not, it basically full of vulnerabilities, it is just waiting for somebody to exploit it.
But if somebody write the code in Python, Python don't have that. So no means
Python, everybody has issues. Python is little stronger type than C program, but every language has same issues.
But they don't have actually this 32-bit.
Right, but when you are running that Python on a specific computer, it forces you to that machine's register size 32 or 64. So, that is basically, so I just wanted to distinguish you something mathematically correct, there is no flaw, something breakable, that is also no flaw. The fallacy connection is when you implement, you basically tie it to the implementation details, that basically mathematicians did not take into account, and from an attacker perspective that is what people look at. Now that it is 32, 64 going through processor to cache, this mathematical guarantee does not look into the cache misses, cache timing, it is completely oblivious of it. When you introduce those features, that makes it vulnerable. So, now that you are done with the counter, so how would you use it? So, whether software, hardware, it is a similar pattern. So, you have to provide this in certain way, whether it is the key size and the key, the mode as counter, non certain value, and what is the counter. If it is a counter mode, you have to give counter start name, and if you are doing a software call, you have to create a file wherever you are putting this, or whatever way it is, you pass those parameter, and this one is simply calling the function from libgcrypt. So, software implementations of all of this is available from libgcrypt, libgcrypt library, and it is quite possible Python has already connected to, it is already connected to Python library. If not, just use libgcrypt.h and all software functions you will be able to call. Compilation would be little issue, because this thing has known issues with compilation error unless you do exact right versions. Nonetheless, when you test them, you basically run with different plain text, ciphertext. Can anybody tell me how do I test a AES module? Let us say software implementation is given, how do I test it? What would be the test case? Remember we talked about verification, how do you verify the functionality? Let us forget about vulnerability, which we will talk in a moment. How do you verify AES module? You know it does encryption. What you do not know, if you encrypt the encrypted message, how that would look like, because 2, when you add 2 plus 3, you expect 5, because you know what 2 plus 3 would be, that is your golden model. There is no golden model. If I give you only one model, just one AES module, how would you test it? I saw a hand, go ahead.
Sir, we can do one thing, we can encrypt first, and when we got the ciphertext, we can decrypt it.
Thank you.
Get the same plain.
Thank you. So, that is why when things looks really, oh my god, how do I do it, it is not 2 plus 3. In elliptic curve cryptography, this will become really complicated, but you simply any message you give, whatever message, this case I gave some message, meet me at the office, any message you give, you encrypt it, create bunch of random zeros and ones, and then you just give that message and call the decryption. Instead of encryption, you call the decryption, and see whether you got your original message. It is as simple as that. Now, how many tests we have to try, whether how to guarantee your implementation is correct, that is different. Wait until I talk about verification and on using Wiki proof. Any question on the usage of AES counter mode? So, you need to have a notion of this. Now, this is where I want to introduce something. Let me go back to security engine. Security engine, and this would be a problem even bigger when you do RSA. RSA key size is 1024 or 2048, it is not 128. And this security engine, when is sitting in this AXB bus, this AXB bus, these are, remember, these are standardized buses, you and I did not design it. So, the company who is selling security engine have no choice, and this bus typically has bandwidth of 32 bits. Now, for security engine to call my AES, routine, can anybody tell me, you are an engineer, tell me what are the engineering issues? By the way, we faced all these issues. So, exactly that is how we know, and our solution is used by commercial tools. What are the issues here? AES understands these stuff, that is why I wrote it down. This needs, I showed you the thing, it needs all these. This particular case we are interested. So, block in, this is 120, this is not the key size, this is the block size. For AES, irrespective of AES 128, 256, all that stuff, block size is 128 bit. So, all these are fixed, they need exactly this thing and start signal 1, and then you have to wait for the done signal, right. So, the question is, how do I transfer all these data? I, as in security engine, I got a request from CPU. How CPU transfer, that is also a little complicated, because these are all memory mapped IO. How many of you know what is memory mapped IO? So, basically for security engine, so if you are thinking that CPU or processor, if you are thinking CPU or processor is simply taking a track and putting everything in that track and sending it, it does not work that way. Even in this bus protocol, or the way the transfer happen, or this security engine, the way you want to visualize this, there is a piece of memory based on this transfer. How this happens I will not talk, I will explain the same thing on this bus. So, there are locations from certain address 000 to 111, for example, a specific byte or location has a specific meaning, maybe the first one is, and it is all hard coded. First one is key size, second one, or from then on all the bytes are the actual key, then the mode, and so on and so forth. So, therefore, security engine when it is sending the request or AES going to read, it is really not reading from security engine, it is really reading from that memory byte by byte or 4 bytes at a time. So, the question is, if you are reading 4 bytes at a time, but none of them looks like 4 bytes, this is 120, 256, it is really lot of bytes. So, how do you take care of it? Think of you are an engineer working in a company, that is exactly the problem given to you, that you are connected to a bus that can transfer 32 bits in a clock cycle, and you have to transfer all these stuff. How would you do it? Just give me some layman's view, how would you implement it?
Multiple clock cycles.
Multiple clock cycles. So, basically in the community you call it you need to write a wrapper logic. You write another function, and from that function you call this function if you are doing in software, and that wrapper logic need to have a finite state machine. That finite state machine needs to read 32 bit at a time, just to get even just the key itself, it needs 4 cycles. So, it needs to have a finite state machine that counts 4 cycle or 4 states. Only at the 4th beginning of 4th state, then it knows key ready. Then after nonce and all that, it is going to take time. When all of them is done, only then that finite state machine is going to do the start signal 1. Because you have to kind of understand, you are reading from this memory, it is getting 32 bits at it, and this problem is more severe for RSA. When we go, you will talk about 1024 bit key, and nobody uses 1024, 2048 bits key itself for RSA. Anything smaller than that is truly vulnerable. Any questions on this? So, when you go to industry, this is exactly what you are going to face. Your expectation would not be I write a function, I call a function, it works, it will not going to work. So, the wrapper logic is the key idea. And in fact, wrapper logic is very common in security domain. In fact, there are many security engine who actually do monitoring of different component. So, if you are following that convention, story is slightly more complicated. So, think of a CPU, your some kind of controller and all these components you have, all these controllers you have, then you have the security engine. So, one of the objective of security engine, whichever company follows that policy, is that security engine has kind of connectivity to all these places. It is not a great design principle. This is more security unfriendly than, and everybody has a wrapper logic. Anytime dynamically you want to implement certain security protocol, these protocols are getting checked here and security engine updates that. So, for example, this one checks any value coming in has to be a positive integer. Let us say that is what it is checking, negative number they do not like, but 10 days later the company policy changed and maybe the people are getting negative salary, whatever it is. So, then that policy got implemented, right. So, then this security policies and security engine checking those policy. So, the wrapper logic in highly secure environment or the design that are for safety critical system that needs protocol update, security protocol update. So, that is basically the kind of story we deal with. And many of you, those who go to different consulates, different countries consulates, they keep changing their rule. So, you really have to have a wrapper logic. You just do not rely on what your brother or parents, how they got the visa. You kind of understand, okay, what are they expecting now, how many letters, how many forms. So, that is kind of the story. When things keep changing, new, so think of antivirus running, another signature, you know, that checking whatever, when you can dynamically do that, but this has a significant performance bottleneck. Any question on this sorry, on this utilization, getting byte by byte, creating the wrapper logic and then implementing it? Yes, please.
We are introducing wrapper to make performance enhanced.
No, we are introducing wrapper so that two people can talk. This one talks in Bengali, this one talks in Hindi. So, you need an interpreter. Here thing is the bus we use, that is a standardized, that cannot be changed. So, that allows 32 bits per cycle. So, therefore, to transfer all these bytes, 32 bytes, you need at least 4 cycles of transfer. Somebody needs to keep track of it. Did I have the full key? Right. So, that is counter, that FSM, whatever you implement, that software, that is your wrapper or glue logic. Okay, now, the counter mode, Galois counter mode, this is basically used in your TLS protocol. So, basically just this part is new and this part is essentially in layman terms doing the authentication, and the community has a nice name for it, such kind of encryption, authenticated encryption. This is known as authenticated encryption. And if you look at observe this part, this is nothing but your same counter mode. This is exactly same counter mode, no changes. But in addition to that, it is basically generating your authentication output. In addition to your ciphertext, it is creating authentication output. It still has the same thing, it should have same thing, the start, maybe I forgot to write, it still should have start, it should have done and authentication ready and all that stuff. Any questions on, or at least the incremental part of the story? And this is basically using Galois field multiplier, and this also, because it is doing authentication, it needs a hash key. So, it is basically, think of this is an authentication. I did not talk about hashing yet, but think of this is a kind of similar to hashing.
What is happening in the authentication?
So exactly the way any authentication works, you basically get any object or key or anything, you map it to other way around. You get a message, you map it to a key. So, the pointer is other way. You get a message, you point to a key. It gives a unique identifier. whatever the any hashing function, whatever it does, this is lot more secure than that. Whatever SHA does, anytime you hash to a hash table, this is basically Galois field is going to create a tag for that. And instead of using one authentication, one encryption, this is authenticated encryption, you get both out of it. And the XTS I do not believe people uses, but it has all the stuff of previous one. I should be able to show somewhere. This no, it is kind of slightly modified. So, this part is there, then it makes some tweaks, and all of those pre-tweak, post-tweak, all of those are there, and you have your separate encryption and decryption. This is kind of different than previous implementation. In previous implementation, same computation is inverted. You give the ciphertext and the key, it will produce the original message. You give the message and key, it will produce the ciphertext. But here there is a separate encryption and decryption logic, and this is basically cycle stealing. So, now I am going to talk about the next one, which is elliptic curve cryptography. Let me just basically introduce this, and in the post I will talk about the remaining part. So, elliptic curve basically, as you see the name, it basically elliptic curve is a mathematical curve with lot of interesting properties, and the reason these algorithms are secure because of the elliptic curve. And the problem with, before even you talk about designing it, let us talk about testing it. When you have a elliptic curve encryption algorithm, you cannot do the testing we did for the AES. You give any message, you encrypt, you do decrypt, because for you to do this elliptic curve cryptography, you have to give 2 points P and Q, and those 2 points cannot be any random point, they have to be valid point on the card. In fact, for any people who are working many years in the cryptographic domain, it is actually very difficult, we found out painfully. So, what we do, we go to the NIST website, there are a lot of curves, the curve has its name, and there are a lot of points somebody figured out. You just do not bother about it, who figured it out, just go and take those P and Q point if you want to test whether your implementation is right. And basically lot of operations are on P and Q, and elliptic curve basically implements a function similar to this. It does a y square, x cube, and some function of x, a polynomial of this nature, and that could this value could be 0, 1, whatever it is, and that is basically the curve. That is the elliptic curve, and all the operations are on the elliptic curve, and the key idea is finding a point or finding a solution. If you know only one point or the other, you will not be able to figure out the other one, that is the idea. Now, so the elliptic, yes please.
So, what is this curve represent? What is your x axis and y axis?
So, this function, whatever function you choose. So, but the function will have these characteristics, it has to have y square, it has to have x cube, and then it has to have x to the power something, plus minus is fine, and this may or may not have this number, that is really called
Same x value you have 2 y value, right? So,
sorry, say again.
so for same x value,
In this particular example you have 2 y value, yes. So, depending on that function, what that exact function is, so the function would be something similar to this square would be there, that is required, and this cube, this is required, and this is x to the power 1, this is required, and there could be a constant, there could be a constant value here, may not be a constant, plus minus both are fine. So, that is the function of elliptic curve for elliptic curve cryptography. That special class of function this algorithm is designed. Somebody figured out that function is ideal for this, not any other polynomial, that is the exact polynomial it has to be. So, now this was introduced in NIST 1999, and it basically uses modular exponentiation in Galois field. When I talk about RSA, I will zoom into it. Only difference between RSA and elliptic curve is in RSA all these numbers is for normal number, I do not know whatever the mathematical name for it, any of those integers, but here this number has to come from the curve, and that is basically the level of difficulty. And not to mention elliptic curve cryptography is also broken, that is why this post quantum cryptography, which we will talk on Friday.
So what is the plain text? What is the key? Because
So, I will come to that, I will come to that after the thing. So, elliptic curve cryptography has kind of two variations. One is the encryption one, the elliptic curve encryption scheme, and second one is signature DSA, which is authentication, sign and verify scheme. So, when I talk about the encryption scheme, we will talk about the message and key and all that stuff. Thank you, and we will talk about it after the break.
okay, so we'll have 30 minutes break now. 11:30, 11 assembly. We have tea outside. after lunch we'll have the exam first. I think around 16, 17 people.
We are going to talk about different types of cryptographic algorithms. In the previous lecture we looked at AES, and now we are going to look at another algorithm that is named after three scientists who came up with it, RSA, Rivest, Samir and Adelman. And the idea behind this algorithm, or the original algorithm, relies on the fact if there are three numbers involved in a computation, and if you know two of those numbers, you won't be able to figure out the third number. That is basically the key idea. And if you think from a encryption perspective, if you have a message and if you want to encrypt with a key, so this E is the public key of the recipient and it operates on the field. So, this is a modulo n, then you get the message, and if you want to do decryption, then you are basically decrypting using your own private key, which is D, and then you are going to get the original text. And so, these two computation can be summarized here, and this is where the observation I am making, that we are dealing with three numbers here, right. We are dealing with E, D and N, and if you are given only E and N, the modulo operation you are performing, E is the public key, anybody can know about it, and N you know what modulo operation I am doing in the RSA, you will not be able to figure out the private key. That is the key idea, and the way it is computed is actually interesting, because that idea that goes back to that computation. When you go to the key computation, so that is basically I want to highlight for RSA. When you compute the key in the process, so before that I need to talk about, there are four parts of the story in RSA: key generation, which I am going to zoom in, key distribution, encryption and decryption. I will talk about all the components except key distribution, because it is not even a algorithmic story. It is basically how do you, when you have the key, how do you transfer that key to your recipient, whichever secure way you want to transfer. Because remember, we had this fallacy, I do not trust the communication channel, that is why I am sending the message encrypted form, how do I first time send the key. So, that is still an issue, and there are different ways people can communicate, just do not send through email. Maybe you call up, and call is more secure, you give the key, but that still when algorithm is discussed, any algorithm, every component is discussed, which I am not going to talk, that is what it is. But let us talk about key generation, or mostly the most important part. I will take example, this is a lot of equations. So, I do not want to bore with this, I will take an example, you will see, but the most important part is this computing a number n by multiplying two prime numbers. Again, same as the previous assumption I made, if you know two number, you will not be able to do the third number. Now, we are saying even one of the number is derived based on multiplying two prime numbers, and if those prime numbers are large enough, then you will not be able to figure it out using the computing resources of the universe. That is basically was the original assumption, until it got broken by Peter Shor in 1990s, and or not technically broken, I will come to that in a moment. So, I want just you to take a moment and think about, if there are two prime number, no matter how large it is, you can take your calculator out. If somebody give you those two prime number, you can very quickly compute it. So, multiplying is fast. So, this encryption process is fast, but how do you get the prime number? There is a little bit of details of it, but that is fast. But if I give you a number which is multiplication of two prime number, figuring out what are the original number, if I give you the n, for you to figure out what are the p and q, because if you can figure out p and q, you broke that algorithm, right. Now, I will go through other steps, but before that I want you to get a thought about it. What Peter Shor did in 1990, around 1990s. So, Peter Shor and that algorithm classically known by Shor's algorithm, which we will talk briefly on Friday when we talk about post quantum cryptography. Peter Shor said, if there is a quantum computer stable, reliable with large number of qubits, then we would be able to do this integer factorization. So, this algorithm, Peter Shor's algorithm is known as integer, or some people call it prime factorization, but whatever it is, we will be able to do that factorization in no time. So, that is really what started this, that along with few other things started this whole post quantum cryptography domain. But I want you to be aware that we do not have stable quantum computer today, and my last thing I checked, using today's quantum computer, we are able to factor either 21 or 35, I do not know, it was here, maybe the ball has moved here, that is all we can factor today. So, you can imagine in 1990s they were probably factoring 6, that is probably they are factoring, or I do not believe they were factoring that even then. So, we are able to do 21 or 35 in some level now. So, that is really the silliest range, but everybody expects quantum computer to be stable, going to be lot of reliable qubits. Very soon when that happens, this is true. So, this is true, prime factorization is possible, but no matter what it is, the little bit of the story, that story goes. So, in because of 1990 many governments panicked, including US government, and there is a vast majority of in the security algorithms in many of the national security agency and all that are built around RSA. So, if RSA can be broken, then other competing countries would be able to break into the system and figure out everything, and exactly the way this AES, RSA, all those were selected, they go through all competition process. Competition process started, I will give you the full story on Sunday, and a lot of algorithms are gone evaluated, and finally 4 algorithms were selected, and by the time selection was done, somebody already showed side chain analysis will break them. That is the last chapter. But for today's chapter, RSA actually relies on this philosophy. As of today, it is still secure, because these prime numbers are not 7 3 or 7 5, it is not that small, these prime numbers are really large. Any question on this idea of multiplying 2 prime to get the number and factorizing that number is hard. And once you have that 2 prime number and you compute that, then we do totient computation, then we choose a integer such that certain things. So, this choose an integer, that is nothing but the public key for the recipient, and then we determine decomputing the modulo, that is nothing but the private key. So, this is private key computation, this is public key computation, this is basically an intermediate step based on doing LCM or GCD, and this is basically multiplication. So, that is basically the key generation, it generates the key. And here is an example just to make it so. The prime number, let us say we start with prime number 2 prime number p and q, first step is to multiply, we simply multiplied those 2 prime number, then we compute this intermediate step. I am not a cryptographer, so I am not quite sure why this step improves the strength of the algorithm, but no matter what it is, it computes the LCM and basically finds that totient function of 780. Now, the next operation would be on 780, it is choosing a number between 1 and 780 with the property of co-prime property, and it is not, should not be divisible by 780. So, it cannot be 780, and let us say that is 17, that is a co-prime, and then we compute the private. So, this is basically the public key, this is public key, and then it derives the private key by computing by computing the function. Let us see what was the function, it computes the modulo e to the inverse modulo this one. So, it computes that one. So, 17 is right here, and 413 is, I do not know where 413 is right there. Sorry, this it derives 413 modulo 780 to make it 1, that is how 413 is derived. So, that is basically the private key for the sender. So, it follows that procedure to get the keys, and now once we have the keys 17 and 413 we can now encrypt and decrypt the message using the equation I showed earlier. So, for example, if 65 we want to encrypt with the 17 key modulo 3233, that is the n. So, remember in that equation of d, e and n, this is basically, if you are compressing, this is e, this is n and this is d, that is d. And so, basically compressed value for 65 would be 27. So, this is the cipher text, and once you give 2790, it gives you back the original text or plain text. Any questions? So, RSA is basically, at least US government kind of gave it up on RSA, but AES is still widely used, AES 256. RSA I basically talked about to give you the context. So, it had all the right notions in place until Peter Shor came up with this idea. Okay, now we are done with the RSA. So, now from an engineering perspective, if you are going to implement it, in addition to the implementation detail we talked about, this I did not talk about. So, because this has a lot of finite state machines, and finite state machine vulnerability I am going to talk about in the afternoon. So, the designs we have done and delivered to different companies, that is basically you need to have encryption, decryption, you also have to have some level of mitigation. We showed pictorially as a separate one, but in reality they are actually merged. And in terms of usage, or if you are going to call the software function in your RSA module from libgcrypt, you basically going to have the key size of RSA. As I said, nobody uses anything lower than this. So, 2048, 307, mostly people, even the countries who are using RSA these days, they are trying to go for 4096, and then it computes the modulus and exponent that I talked about. Modulo n, that is the modulus, and exponent is to the power e or to the power d, that is basically the computation. Everything else is the input file, which is the data you are trying to compress, and output file, that is your cipher text, and the operation you can do is either encrypt or decrypt. Any question on designing this or invoking this when you have this implementation? How do you invoke RSA? All right. So, now we are going to talk about, I am going to change little order and talk about SHA, because everybody else is using the hashing function. So, before I talk about SHA, how many of you know what is hashing? What is it used for?
Sir, it is used for integrating purpose, like we have a hash function which states that it should be collision resistance, it should don't have the first pre-image, second pre-image, it should be unique so that we cannot go the reverse.
Absolutely. So, when you have any piece of information, any name, any values, any text, you are basically trying to compute something out of it, ideally unique number, not a situation like this where two of them map to the same value, so that somebody can compute. When you send it and whoever receives it, they can compute the hash, and when you are sending this message, think of this as a message. So, you are sending the message and also sending the hash, and whoever receives the message will compute the hash of message and tries to figure out are they equal, just to make sure nothing got lost in translation. Hash is a very mathematical nice way. In the early days, people used to send parity, number of ones, even or odd, checksum, and in fact, I am going to talk about a hashing technique. In fact, one of the MD5, that is really the checksum. You just compute, sum them up in some way and come up with a number, and the recipient also computes, it is going to produce uniquely the same value if you invoke the same function. So, somebody to scam with this technique, they have to make sure somehow there is a collision in the hash function, it has to create. And so, basically two places hash is compute on the sender side, the hash would be computed on the sender side, hash would be computed on the recipient side. It is supposed to produce the same unique value, assuming the message is not altered. Even if a single bit is altered, it is supposed to produce a totally different value. That is the idea of hashing. And today the hashing function that is used in transport layer security is SHA-2. It is slightly different variation of original SHA, but it is as you can see, this mapping process is kind of lot of rounds and lot of uniques and then XOR and all that. So, you take a message, you compute all these transformation, and the key idea is so that you can create a unique number out of it. That is the whole idea, one unique number. Of course, few things you can always figure out, that collision is not allowed, two messages should not produce the same key, that is not allowed. What is also kind of implied, the number of messages you are sending, that number of messages 0 to I, the messages you are generating, the number, your key space should be equal to at least number of messages plus 1. I mean, equal will work, but that is basically the expectation. So, whatever the key space, whether it is a natural number, if you are doing and if you are representing with a 32-bit number, then your space is 2 to the power 32. Is the number of messages, number of packet, whatever level you are trying to do this thing, you want to make sure the number of messages does not become, or number of packets does not become more than 2 to the power 32. I do not believe anybody will create a hash table of 2 to the power 32, that is so large, even managing, reading, it will be nightmare, but these are the two key requirements when anything is designed, no matter what transformation you do. So, all of this transformation is essentially trying to make sure, carefully designed, that you do not produce the same key given two messages, even 1 bit difference. Any questions?
So, for a given message the keys are unique, or it can be same key you can apply for different messages?
No, given message key is unique.
And you are adding 64 keys.
So, this particular one I need to look at, but it is basically one key. Sorry. The output I am treating it as the result I thought as a key, but this hash function is unique. This hash function is unique, key is not unique, key is same. Hash function is given a message, the output hash function is unique. Now, so for this SAR algorithm, basically 3 versions of SAR is available. Our implementation gives a reconfigurable version, arrow moved little bit. Configurable thing in the software you can do that, hardware that is not kind of desired. So, 256, 384 and 512. So, that is basically the 3 variations of SAR that and in fact, software if you do the libgcrypt, that also provides 3 functions of this SAR2 implementation. And the way you use, again the same thing, you give a message as input, you get the hash function as output, and you choose basically what key sizes you are going to opt for while you are doing the hashing. So, in the SAR category, actually the regular SAR is not used in transport layer protocol. What is used is known as hash based message authentication code. It is little more so this should have been SAR2. It is little more complicated, and as you can see, XOR is a very interesting operation in security domain. Wherever they get a chance, they put a XOR. So, it is little more stronger in theoretical guarantee compared to normal SAR2. So, really people use SAR2 with HMAC, SAR with HMAC, message authentication code, and HMAC implementation. Again, as you can see, HMAC is essentially a function which uses SAR 256 in this example to implement the HMAC, and that is basically this one is actually used in transport layer security. So, extra thing is all these operations, and I am not exactly clear how much it increases strength, extra amount of padding. Even the original SAR you have the notion of padding, but the required assumption is padding in the sender side and receiver side should be consistent. Recipient know what padding you have used, extra level of padding, extra level of OR, and then there are few layer of extra hashing, some extra movement, and that is the community kind of use, and the assumption is this is much stronger scenario with less probability of collision compared to traditional SAR2. So, now I am going to talk about random number generator, and random number generator is essentially kind of used almost every cryptographic algorithm in some form or the other. Maybe I did not highlight it, from now on I will highlight, and this was our implementation, deterministic random bit generation and then manipulating it in some form. But in reality, if the random number, when you generate random number through any mechanism, here we are using the SRAM memory entropy, but any mechanism, by default random number generation is actually pseudo random generation, although all the guarantees that the cryptographic algorithm gives it based on the assumption of true random number generator. So, let us try to make a distinction between this pseudo versus true random number generator. Let me ask this question: any of you know what is the difference between pseudo random number generator and true random number generator? Yes, please.
For zero random number generators, we take a seed number, randomly seed. So if we know that seed number, we can make any number there. And true random number, we have no seed number. We can generate any number.
Absolutely. So, today all the, that is absolutely correct. So, today all the generator that you have that you invoke through your software program, for example, in a C you have this rand function, similarly Verilog VHDL have similar functions, they are all pseudo random generator, and some function may not take a seed, but they are internally taking a seed if you do not provide, but normally you provide a seed, let us just say you are providing 53, whatever seed you provide. So, there is a good side of it, bad side of it. The bad side is because it takes a seed, it generates a sequence of number, and if you call it again with the same seed, it will give you exact same sequence of number. That is why it is called pseudo random number generator, because if it was really random, every time you call it, it should never produce the same number again. So, you cannot use pseudo random number generator to generate a nonce unless you can ensure same seed will never appear. So, then question is, that is the bad side, that you give the same seed, the sequence of number, let us say A, B, C, D, whatever the number you are generating, if you give the same seed, it is going to produce exactly A, B, C and D if you start from there. In a for loop, for example, you are generating, it would give same number. So, that is a bad thing, because the cryptographic algorithm guarantees are based on true random number. If they are not really true, it is not a good news. What is the good side of pseudo random number generator? It is a handicap, but it helps somebody. Whom does it help? All of us, because if pseudo random number generator was true, then you found a bug, you went to your manager to say, oh, I found a bug, next time you run, it is not, that bug will not exist. You will not be able to reproduce that bug, because every time anything happening, if your program has a random call, most likely it is, if it is a million line code, it is going to produce a unique number, it will take a different path of execution and that bug will not happen. Because it is a pseudo, you start with the same thing, do the same process, you will the bug becomes repeatable, vulnerability becomes repeatable. Many other reasons will block it. Sometimes we do face that you run the something and you wanted to show it to somebody, you went to a doctor and your health problem does not appear to be, you come home again, you have the health problem, right. So, that is basically the issue, but either way random number generator, how you implement, it all boils down to what is your source, and I will talk about one kind of random number or generator using Prof. What is your source and what is the entropy. So, when you generate a set of numbers, there are mechanisms to measure the entropy of those numbers, how unique they are, how different they are, right. So, there are a lot of metrics I am not going to talk about, but the important part is what is your source, is that source truly random, that is really what it is, right. So, when you kind of call a rand function, where even if you are tossing a coin, the coin will have some bias, may have a bias, although assumption is when you play any game, you have a 6 roll dice and you throw it, your probability would be always 1 over 6, 1 over 8, 1 over 2, whatever the probability is, but that would not going to work. And in fact, how many of you know coin tossing actually is not random? Why it's not random?
Because it is every time we toss a coin upon the side of head, it will fall down the head.
So, basically some of the reason we believed it to be random, because we did not account for the environmental effects, the height from the floor, the force you provide, whether there is any wind or air. If you control all of them to be the perfect, outcome would be exactly same every time. So, in early days we used to call that as a bias coin, but there is no such thing as bias coin. Tossing a coin is not random at all. If you control everything exactly same, the force you provide, the height you throw, the height you are, and whatever you are letting it fall, it would be always the same. I have done it hundreds of times, it always falls on the same side. If you control it right. So, because we used to call it random because outcome we were seeing, but what you did not observe, all the individual events happening, it is not the coin that has that property, it is just the way you are throwing. Every time you put a different force, it may go different height, different number of rotation and all that stuff. So, that is basically was causing the issue, but either way the entropy that you calculate or the entropy source, earlier entropy source was tossing the coin and the amount of force you provide, height and weight and torque. So, that is kind of important, and I am going to talk about one of those. Okay, Prof I will talk later. So, I will come to that. Let us go back to elliptic curve cryptography, but when I talk about Prof I will talk about another source, process variation, which appeared to be more random. But today there are companies, at least there are 6 solutions from 6 companies that give quantum random number generator, and their philosophy is the quantum phenomena is truly random, which appears to be because it based on certain spin or device, but that is how it appeared to be the tossing the coin. Everybody was thinking that way, and when it did not work that way, people used to think the coin is biased, right, like the Soleil movie. But here in case of quantum, at least people are explaining because it is based on physics, and that is a really physics phenomena which is a random phenomena, that is why it is a quantum. So, there are quantum solution, quantum random number generator. So, if the quantum random generator is so interesting, why, how come everybody is not using it? It is so interesting, and cryptography relies on a true random number generator. We have a solution company selling it, why everybody is not using it? It is expensive, one thing, it is integrating, quantum being unreliable, the company who are selling, they will be saying every whole world is perfect, of course, but because integration of classical and quantum is not a piece of cake, I just leave at that. So, last time we started talking about elliptic curve crypto systems, and we talked about elliptic curve, and its exact behavior has to be y square equal to x cube plus a x plus b. So, a and b can be changed, but the polynomial has to remain the same. So, all the guarantees on elliptic curve cryptography is based on this polynomial. If you do another polynomial, it would be another, and the algorithm I am going to talk about, it is all about P and Q, all about 2 points on the curve, and in fact there are similar algorithms something. So, from the RSA algorithm, RSA is Samir's secret sharing is also based on a similar idea, where if you have a polynomial or this kind of a curve, and if the points you kind of share, if you have multiple party you are sharing and everybody knows, if everybody knows all the points except one, they will still not be able to derive the secret or the key. So, key is constructed using multiple points in Sumit secret sharing. So, if this is your polynomial, so there are multiple points that are used, and each point belongs to one of the parties in the story of communication, and multiple points are used to compute the key, and unless somebody knows all the points, they will not be able to derive the key. And who knows all the points? Somebody who bribed all of them. If everybody is malicious, then why are you talking about guarantee? But the guarantee in Sumit secret sharing goes as, if you do not know even one of them, if not compromised, then you will not be able to construct the full story. But this particular one is about 2 point P and Q, and just getting. So, it is basically when you are deriving the shared secret to derive the key exactly the way RSA derived the key D and E, those 2 points will be and has to be on the, in fact sign and verify also are these point on the curve and does this have certain properties, then that is how it check. And in the early days, even 10-15 years ago, people used to think this is unbreakable before post quantum cryptography days. So, this I briefly talked about. Let us move into kind of each of the item. So, first one is the ECIES, elliptic curve encryption. So, elliptic curve you can do encryption, you can also do authentication, sign and verify. This is for the encryption. So, it looks little convoluted, but this is actually simple. So, you generate a random number and this G is basically, so the polynomial, the elliptic curve has few parameters, G is one of them. So, G comes from the elliptic curve, and then you calculate R based on a random number small r. You calculate R, and the output that it is going to produce this R, the ciphertext C, and the message authentication code, that is D. So, this is really doing authenticated encryption, not just pure encryption like AES counter mode. This is more like AES GCM mode. So, only thing this procedure then encryption involves, how do I get R, that is the first step, how do I get C, this is the fourth step, and how do I get D, that is basically you call the message authentication code using the this stuff, and that is derived here from the 2 points on the curve. We are getting a point derives a shared secret, it basically derive it using this R and the key value, and P is not equal to O, and it gets the symmetric encryption key. This is the key derivation function. So, this is basically derives the secret, and there are details beyond my understanding. It derives that secret, and then that becomes the key, then you use that as a key and give your message to get the ciphertext. So, this logic is exactly same in every encryption philosophy. Only thing difference is how do you derive the key. In case of RSA, you multiply 2 prime number, do one more computation. Here you basically operate on the elliptic curve and then compute the key derivation function on the elliptic curve to get the key, and then you use that key to. So, it basically derives 2 keys, one for the encryption, one for the authentication. Any questions, how do you use elliptic curve cryptography? And decryption is exactly inverse. So, basically R, C and D comes in, this is the message authentication code, this is the ciphertext, this is that derivation from the random number, and it again derives the shared secret because it is the dual of it. So, it is going to get the same one P x, and then basically it derives the key again. It is supposed to, key derivation function is supposed to produce the same key and key m. So, it computes the message authentication code, and if the message authentication code does not match with the D that came in, then you know there was an integrity violation, it is not the same, and then similarly finally you basically derive the message uses the encryption key. And so, this is basically symmetric key cryptography, same as AES. Only thing is, in case of AES you will actually have the key, you do not derive it, here you derive it from the elliptic curve. And testing this becomes problematic because finding valid points, starting the testing itself is become a problem. So, what we did, we went to the NIST website that divides for different type of curve. So, if I go forward, I will show you what type of curves exist. There are known curves, and each curve has a key size. So, you do not choose the key size like AES, you can choose any key size and any algorithm, any mode. Here you cannot do that. Once you choose a curve, your key size is fixed.
Like encryption algorithm is what kind of encryption, or any encryption will do the key function?
So, this encryption algorithm I do not think any encryption, this has its own encryption algorithm. This probably, give me a moment, it actually have it there. Oh, sorry, it is AES counter mode, it uses AES counter mode in the definition. Key derivation function is the hashing, message authentication code is SA HMAC, and then elliptic curve cryptography is the wrapper around it, basically it calls everybody else. So, I wanted to put encryption and decryption side by side to show you this is actually, before I say anything wrong, this is actually carbon copy, only thing swapped is the output cipher text is here and input message is here. Other than that, everything looks identical, including curve parameter, generator, point, and all that stuff. Yes, please.
So this is more like a common question for the RSA as well as this. So during the encryption process or decryption, we are using that message. Now, is it that that message is being encrypted in parts like a block cipher does, or the complete thing is converted into a long bit string?
Right. So, for AES it is fixed 128 bit, it fixed. This one I need to look at. So, this implementation actually we allowed 128 into 56. So, I am not sure whether that is the, so there are only two choices, this is reconfigurable, but AES by law it has to be 128. But here we use two of them, whether the guarantees actually allow other size I do not know, but it has to be a fixed size, because when you are kind of doing, remember we are using AES counter mode. So, it has to be a block cipher, it has to be variable size. I do not believe any encryption algorithm can do that. In a block cipher you kind of do it that particular way. And yes, please.
If we are having variable size, then we can introduce one-time padding in that.
No, variable size, if it is smaller than the key size you can do one time padding, if it is larger than key size then it actually does not make any sense, right. So, it still kind of has to be some form of kind of blocking kind of boundary. So, this one I just wanted to show you for software call, software implementation, this is exactly how it is implemented even in libgcrypt. But for hardware, I hope you have realized it by now, this is a bad idea. Can anybody tell me, if I implement this way, exactly this way in hardware, why it is a bad idea, very bad idea? You are not seeing, yes please.
Sir, we will have to introduce each and every component in the hardware, and it will get through the overhead.
Huge overhead. You have a AES counter sitting in the encryption unit, AES counter sitting in the decryption unit, and if you recall SA HMAC might be used by other people, whoever needs it, everybody has their in their implementation hardware part. That is why if you recall the bus I talked about. So, really the way it is implemented, security engine, this is ARM, AMBA, AXB, whatever the secure bus, everybody is hanging here, SA is hanging here, TRNG is hanging there, AES is hanging there, and then ECC or ECIES would be hanging there. So, basically, but this is going to be a bare metal ECIS, the ECC component. These need to make request to the bus to request to come to, let me use a different color, request need to come from here to the SA, to when it is doing this component, request should come and result should go back. If it needs AES counter, then request need to again come through the bus, go through the AES and result need to go back. All these need to be controlled through the finite state machine or the wrapper logic. So, that is how it is implemented in all commercial products. Nobody puts multiple copy, although I shown the this particular way, this is actually same implementation, sign and verify same implementation, only input output is slightly reconfigurable. But for the other ones, this MAC, AES, as I go along you will see these two modules are pretty much used everywhere, almost every routine, and you do not want that hardware to be part of everybody, there would be same component. But this goes to the normal classical logic, how frequently these are used. If every possible cryptographic IP is using AES and you have one copy of it, then it is going to be a resource hazard, structural hazard. So, those are the decision the designers need to take, system designers need to take. Do I keep one copy of AES hanging that everybody else can use and make request. Think of in a processor pipeline you have only one adder and everybody is accessing it. Even multiplier is also doing repeated addition as a multiplication, then it will become a nightmare. Multiply instruction would be stalled, add instruction would be stalled, subtract is implemented as a 2's complement addition, it also gets stalled. So, those issues needs to be also resolved and decision needs to be made, but most industry implement exactly this way. Any other questions? Yes, please.
One more idea that on the hardware level, it is possible that environmental conditions should also change the components of encryption and decryption.
How would environmental conditions change?
Suppose that I am having a AES in a CTR and adders are there. Due to environmental conditions, some adders maybe change some bits and the whole encryption process will produce some false results.
Okay. So, you are saying the computation inside AES itself is unreliable, that we will talk when you talk about vulnerability analysis. Right now, we have to assume AES is working right when you talk about elliptic curve cryptography, because it relies on it. So, this is basically what is showing AES and SI is hanging outside, that is ECC CIS core is sitting somewhere, and so basically actually our original implementation was exactly like that. Some people smiled at us and then we got the point. So, unless you work with industry you actually do not know what happens. So, when you have ECIS usage, you have same stuff, your original message and output, but then key sizes, this key size is interesting for elliptic curve, different than other. So, there are curves defined elliptic curve. If you are taking the curve exact name P192, then you have to use 192 key bits. If you are using P124, for these two curves 25519 and Edwards 25519, for this key size is 256. Those two 256, this one 192, this is 224, this is 256, this is 384 and this is 521. None not it's important to mention this is the strongest curve P221, but this is very expensive. So, TLS layer I believe uses this one, this curve, either this or, because those two are very expensive, P384 and P521, right. Any questions? And the hash function also you choose 256, 384, 512. This is actually not a typo. 521 is not a typo. It is not a 512 written as 521. These are the exact curve. Again, visit the NIST site. It will show you the curve and all these operations and all that stuff. So, now I am done with the encryption. Now, I am going to talk about the digital signature algorithm, which is sign and verify, which is what you are going to use for integrity check. And again the same thing as the CIS. So, you have the elliptic curve base point, that is basically G, and then integer of order G. So, all these assumptions are exactly same, but so it has two parts, the sign part and the verify part. For the sign part, first thing it does is hash using the SHA-2 HMAC, it computes the hash and then does some transformation, a set of transformation, and then it creates the signature pair R and S. A set of transformation, and R is calculated based on the original number, S is, so R gets computed, never mind how it is computed, but basically it computes R and S, and those two values would be passed as the unlike in SA or any other, you send only one message authentication code, here you send two numbers R and S as the valid signature. And in the recipient side I will talk about. So, in the sign function, so ECC is the top level, it needs a random number generator and it computes modulo multiplicative inverse, that is really this function when it is computing this k in the inverse function, and it needs the hash, that is basically the first step to compute the first step. So, those are the components we kind of designed, and then it basically produces R and S values. And software algorithm, when you do software algorithm for ECDSA, it does the exactly same. And as I said, in real implementation, the cryptographic core is inside SA, TRNG, all are hanging on the bus, not on the side of this block, it is on the bus. So, the verify is exactly the inverse, with R and S comes as a input, and the signature check basically checks whether if R is equal to x 1 modulo n, it is invalid, otherwise it goes through a set of checks. And the functionality is exactly the same, only the output at input converted. So, here output only is verified or basically failed, 1 or 0. So, when done signal is 1, you basically check whether that line is 1 or 0, that is basically done or verified. So, again in the implementation psi is going to sit outside or on the bus, interacts through the wrapper logic, and in terms of usage exactly same as ECIS, as you can see. So, SA 384512 and different curves, and the key sizes are determined based on the curve. Only thing is, in the previous example I did not highlight, in the ECIS you have encrypt or decrypt operation, here you have sign or verify. Are you signing or are you verifying? Because all these are important. So, when you download the libgcrypt and run those software cryptographic library, these are the exact switches. So, now I am going to talk about physical unclonable function, and the key idea is, so it has two objectives. One is key management, key distribution, key generation, those are really complicated stuff, and different algorithms trying to do differently, and that is one thing. And then also generating random number is a serious problem. So, Prof tries to solve that problem. So, secret key management and where do you store, how do you ensure wherever you store it, whether the processor is storing in the closest register, is this secure enough. So, the idea is, do you store in a secure place or do you generate when it is needed, and if you generate, how do you ensure the uniqueness, how do you do random, that is basically the Prof route. And in the Prof route, the idea that is used is process variation. So, process variation, if you wanted to manufacture or fabricate a bunch of line on the CMOS in a photolithography, this is exactly what you wanted, very nice sharp edges, this is what you wanted, but what landed up happening, those sharp edges are not there, it got somewhere it is thinner, somewhere thicker, and because of that the parasitics, or if you think of effective capacitance that it formed or created, the size is different. So, therefore, charging and discharging time is different. If you created multiple AND gates, millions of AND gate, each of them would have a different delay. Now, the question is, if everybody has a different delay, how does it work? That is a totally different discussion. The way it works, if you have let us say 2 AND gate between here and there in the path, when you decide your clock cycle, you not only figure out how much it takes, let us say this is take 1.0 nanosecond and this take 1.1 nanosecond, you just add them up, and then in addition you add process variation, because this is the variation during manufacturing. There might be variation when it is running, when it is heating up. When it is heating up, this 1.0 might become 1.1, this might become 1.3. So, you have to account for that also. When it is running, the temperature stuff, and then you have to add it up, and then if this is becoming 2.4, then you have to add clock skew and all that. Let us say that is 2.5 nanosecond. So, then your real clock is 1 divided by 2.5 nanosecond. That is how you decide. So, you account for that process variation, you are willing to give up performance, that is how it works. But for this work, physically unclonable function, the idea is if every AND gate is different, every gate, every multiplexer, every flip flop, everything is different, then the question is that variation is unique. That is really the assumption here. If that assumption is wrong, everything else is wrong. If that is unique, maybe the angle here, how do we compute that, that is different, I am just making it up. Then if you take couple of such gates, how many, which one, from where, and computing a number, that number expected to be random. That is the key idea of physically unclonable function. Of course, people have used it in various ways. Some people are not looking at AND gate, they are looking at the memory cells, SRAM memory and all that, and looking at the variations there to kind of, some people are trying to take the delay variation, some people are looking at the parasitic variation, but no matter what it is, the idea is it is a unique number. Now that it is a unique number, you can use it as a key. If you want to use it as a random number generator, and a lot of research has shown the entropy happens to be very high, and that is it. So, PUF, exactly the way each of the area in security domain is important, PUF has its own area of research. How do you design efficient, fast, physically unclonable function which is efficient to derive, and it does not have all these shortcomings of other random number generators or key generators and maintainers. Any questions on PUF? So, for our implementation of PUF, this is of course not the best one. We are looking at the taking the SRAM memory which is already implemented in the design, and it is basically getting certain information from there, and that information through few other transformation, and in the we are using also elliptic curve there to generate the PUF signature out of it. Of course, there are many others. So, before I conclude, I wanted to introduce few other components that people put in their devices which I did not know until I started working, and one of them is odometer. So, the idea of odometer is somewhat similar to the odometer in the car, how many miles you have driven, and in early days you can actually very easily rotate something and reduce the change the thing. These days it is not easy, it is still doable, but this is the same thing. So, there are multiple classes of odometer, many of them basically use the life cycle odometer would be similar to the odometer in the car. Boot odometer, as the name suggests, is used during the booting process, secure boot, when you are first starting your computer, or when you are doing the firmware upgrade. During the secure operation, can we keep track of what happened, how many times it happened. And so, basically the idea is uses little bit of analog logic here. So, antifuse based boot odometer, it can count basically boot cycle in a secure device, when boot is going on, how long it, because remember during booting time you have minimal resource that you can rely on. Boot is a very privileged operation. You are installing a operating system, first you do not know the operating system is wrong. So, anything you are counting, anything you are doing, all of them has to be secure and on chip. So, this basically gives that on chip, think of this as kind of a clock cycle generator if you may. So, it gives you that ability, and there is a one time programmable memory. So, this one time is important, it is a one time deal, nobody can just go in and modify whatever it is, and that programming is actually done during manufacturing time and gets sealed, and that gives certain piece of information to this one, and then we have certain types of address generation, encoding and computation to kind of get this tamper resistant tracking of early life cycle of the device, and this is typically designed for one time only. The first time when it manufactured, come to the company's facility, you want to do the installation in a secure manner before you release to the market. This is just one time deal. A variation of that is basically for the life cycle of it. Some companies use the same odometer, once for the beginning, other time for the one, and this typically in our implementation we used a ring oscillator based life cycle odometer. So, key idea is we can measure and report the age of the device. How do you do it? So, lot of other implementation we have looked around, some people look at the aging of certain elements in that chip. If you know what are getting implemented and you have some idea of how to do that, but remember all of that has to be done very quickly. It is not like you look at a trunk of a tree and count the number of rings, and then you kind of figure out how many years the tree is old, which is fine. Even certain element people do carbon dating, we do not have a lab experiment set up there to a carbon dating, but certain features, process variation, all that stuff, and then from that measurable aspect some people do. But we basically look at the ring oscillator, and basically on the ring oscillator there is a phenomena called negative bias temperature instability. So, we basically make use of that, and then of course, there are some sensors and that sensor reading. Assumption is all of those are correct, the ring oscillators are correct, and the instability that mathematically defined on them, that is working fine, sensors are working fine. So, we have access to those sensors, and then basically you can control how many stages of these ring oscillators are there, and based on that it produces a 32-bit number. Of course, 32-bit number is not too large, but nonetheless that gives you that aging information. And most of the time this is used primarily when this boot odometer says 100,000 miles have been driven, then probably you do not want to drive that car. It is basically used for that. Any question on this odometer, whether boot odometer or life cycle odometer? Yes, please. So, do not worry about these blocks, this is exact names I gave, but it has also your different type of logic and FSM and what is the other stuff, the RAPAL logic, all this stuff. So, basically all the information that you are coming in, many of the information I cannot provide, but whatever information comes in, whichever sources you are attached to, you basically take that information and convert it in the form. Remember, this is a digital logic, this is analog ring oscillator. So, you just feed it to in that format, that is what it is decoding. That is all I have for today. Thank you. the second one. যেরকম হবে সেরকম দেখা যাবে।
Okay, so good.
Good afternoon. In this lecture, we are going to talk about the different vulnerability analysis and mitigation of cryptographic libraries. So, specifically in the previous lecture, we talked about how to design and integrate different cryptographic modules and how does it fits into the big picture. Now, we are going to talk about if you are a designer who is designing it, how do you analyze whether it has any security vulnerabilities and flaws, and we are going to talk about different ways of looking at it, and all of these ideas you already know. It's just that today's lecture I am going to focus or apply those ideas on the cryptographic libraries only. So, to be specifically what I am going to focusing on, this is a summary, whether you are developing hardware cryptographic IPs or which people call as accelerator once you implement, or software cryptographic IPs, the different key sizes, they have a set of known vulnerability. So, for example, in AES in software version, the reuse of nonce is a well known vulnerability, and similarly counter overflow, empty, initialization vector, timing, fault injection. In contrast, in the hardware side, you will have some of the similar things as well as you will have ideas like power side channel, timing side channel, clock and reset vulnerability on all that stuff, and some of those are not applicable for software domain. Some of them are common, some of them are not common. And in the security community, this true random number generator, PUF, odometer, they are typically not preferred as cryptographic module, they are referred as security primitives, but whatever it is, they also have their own vulnerabilities. For example, random number generator is basically based on entropy. If for any reason somebody can reduce the entropy based on certain types of attack, then that is going to be a problem. Fault injection would be another type of attack, signature bias, verification, low resolution fault injection, and so on and so forth. So, objective of a designer is then basically can we do iterative refinement. So, you design something, then you know the vulnerability, you implement that mitigation, then you check your vulnerability and tool analysis again to make sure that the security strength has improved, whatever your metric is. So, what I am going to talk about, what are the analysis tools people use or should use, and then what are the metrics. So, I am going to talk about lot of vulnerabilities, but our context is still the same. You have your system, firmware, hardware, primary focus would be security engine or cryptographic IP in this discussion, but as you know these techniques are useful for any of the other modules as well. So, let us start with Google Witchy Proof project. So, how many of you know what is Witchy proof? Although it has a proof, it has nothing to do with the verification. Witchy proof is this one, it is a smallest mountain in the world, it is 42-meter height. This particular one picture did not come correctly. So, that is Witchy proof, and again this picture has nothing to do with Google Witchy proof project. Google's view was, instead of trying to solve everything and fail flat in the on the face, let us try to solve something that is tractable, achievable, and we can solve it. So, all the interesting stuff ends right there, and so if you go to this GitHub page, they maintained a set of tests, and I kind of last I counted it is around hundreds of tests, and what that test gives you, if you have a set of software libraries, you might be downloading from libgcrypt. Let me say it again, libgcrypt library, GitHub page. If you download those, or you design on your own, or whatever you do, as long as it is a software library, those tests will work, and you want to run those tests on your cryptographic library to make sure at least it does not have the well known problems. That is basically the idea of these tests. These are not formal verification, these are simulation tests, but nonetheless it is all at least check some of the bare minimum requirements. So, for example, for of course, some of them are applicable. So, for example, for elliptic curve cryptography, it is invalid curve. You are giving the point or giving a curve, that is not a valid curve, and the nonces, if the nonces has kind of low entropy, those are biased nonces, and there are well known list of attacks. I can't even pronounce it, I will not even try. So, there are many more, about hundreds of tests, each is unique, and that basically covers all the well known attacks on cryptographic library, at least software versions. Any question on Witchy proof project? So, if you are planning to download or write, this is the starting point, then you can test on your own. Now, this one is easy. So, I wanted to start malicious implants. Anybody remember the synonym of malicious implant in software? What is it, and hardware what is it? That would be the question on Friday. Malware for software. Who can say what is the synonym in hardware? Hardware Trojan, right. So, for the malicious implant, for the hardware we kind of looked at it. There are different types of Trojan. This is combinational, this is sequential, this is information leakage, this is and so on and so forth. That is a system level Trojan. So, then for cryptographic library, what you want to do? You want to scan for those, and when you scan for those and you believe you have a mitigation for it, which I will talk in a moment, that scanning tool you want to use it again, just to make sure your metric improved. And what kind of metrics people normally use? We talked about it, number of activated rare nodes, assumption threat model is rareness is the number of rare nodes, number of rare branches, number of rare triggers, and so on and so forth. And then you basically want to kind of on a security level, you want to figure out where your that module is, cryptographic module is, and then you do the mitigation to kind of take care of it, right. Now, anybody knows, if I know this number is not good, how do you reduce number of rare node? What can we do? If there are rare nodes, there are rare nodes, that is the property of the design. What can we do? Didn't we talked about rareness reduction as a technique? One of the objective of rareness reduction, there were two techniques we talked about, at least two. One is area optimization. If you can synthesize it for the least area, that is guaranteed to have the less rareness, which basically means it would create non-rare nodes among all possible synthesis methods. We also talked about design diversity, maybe another implementation, instead of carry look ahead adder, you might want to consider ripple carry adder if it has less rareness. So, similarly there are different other ways of solving this problem, but no matter what mitigation you do, you still want to run the same tool, same technique to make sure you are somehow improving and going towards this line. That is basically the objective. Now, the way in cryptographic module people use, of course, your threat, based on your threat model you figure out what your suspect candidate, and remember it does not have to be rare, because each of the steps are independent. You can manually add some more signals if the designer said I believe this is where I suspect something might happen, this came from some part of the world, or if you believe that if an attacker knows you are only focusing on rareness, they want to focus on rare as well as little bit of non rare. Of course, the space is huge, millions, but if you want to put some of the non rare nodes, that is fine too, that is your starting set. For different techniques that I talked about, different ways of whether it is statistical, whether it is SAT solving, whether it is ATPG, different ways. Once you have suspicious signals as input, different ways you can generate the test. Now, you have basically golden model and your implementation, whatever implementation you compare and you check for output. Now, first question, for comparing output we need a golden model. Where is the golden model in cryptographic story? Did we talk anything that gave you a feeling we have two models anywhere? If you are developing a elliptic curve model, all you have that VHDL Verilog description, where is your second model? Did we talk anything? No? Did not I say 20 times leave G crypt? So, you can use your software model here and you can use your hardware model here, that is how the community uses it actually, because this one is very stable, all over the world people used it. Hardware models are not available, every company develops those, they sell it, they make money out of it. So, you are going to implement on your own, and if you are going to implement that, the problem is likely to be here compared to there. So, it is relatively golden. So, that is and because input output all that is fine, primary thing is message and encrypted version. No matter what nonce you use and whatever you do, the encrypted version is going to be exactly same if key is going to be same, right. So, any questions on this idea? We have the golden model, we have implementation whatever you have, and then if you have another golden model, that is fine too. So, for example, you developed a VHDL Verilog code, you tested for 6 months and then you sent it for synthesis to third party, or you sent it for fabrication and fabricated chip came in. So, something you have a actual silicon running and you have VHDL Verilog model running, you can do that too. It is just that do not try running same time, this is going to run at gigahertz and simulation is going to be at megahertz. It is just that you compare the final result. So, this technology is going to work only in one scenario of Trojan scenario. We talked about so many possible scenario. Anybody remembers in what scenario it will work or what type of Trojans it would work? If you recall, Trojan has different types of trigger and payload. The payload of functional change is the only one where it is applicable. A Trojan that changes the functionality. If it does not change the functionality, you have nothing to compare. If it changes a power footprint, then probably you have to do the power difference, which would be a side chain analysis. Now, I am going to talk about finite state machine vulnerability. If you looked at it, the cryptographic module itself has finite state machine, each of them, because they have different states. Yes, please.
If it is not functional change, how do you basically detect the other kind of Trojan? So, question is for functional change Trojan, it is easy to detect, right? It is not easy, but at least you have a chance to detect. But what about the other kind of Trojan that does not change the functionality?
So, let us take any other example. So, in the Trojan case we have different types of payload, right. So, let us write it out. We had payload of functional change or functionality, that is what we talked about, and then we have the parametric changes. We have parametric changes, you have many other. So, some of the parametric one, for example, it changes the power or thermal profile. So, if it is a power profile, then your comparison should be power. but then you need to have a golden model. Problem is most of the time golden model does not exist, because you need a golden hardware model. If somebody fabricated already a golden hardware, why on earth they will go and fabricate another non-golden one, right. The way people normally look at that, even try to solve that problem, that people do not fabricate all the millions of chips at the same time. The first batch they probably fabricate 5, 10, 20 or 100, and then they kind of do testing and all that stuff, and those are assumed to be golden. They are very carefully crafted, very customized purchase. Instead of when they are asking for millions and billions, things may go wrong. But otherwise this is kind of, that becomes tricky, that becomes an academic exercise. That is why half of the world do not believe in this in the first place. So, now for the finite state machine vulnerability, it is important, because if you look at any cryptographic algorithm, it goes in multiple rounds or phases. Even in AES with 128 of 10 rounds, those 10 rounds is actually 10 state in a finite state machine. There is no other way you can implement it. You have to have, whether you are writing case statements or whatever equivalent in your VHDL or Verilog, case basically round 1, case round 2 and so on so forth, all the way of round 10. You do not jump to round 10 unless you have done R1 through R9. So, therefore, there has to be some signal, some if statement, whatever way you implemented, it is going to be a finite state machine. So, here is a simplified version, instead of 10 round, it is basically wait and wait for data, initial round, and then in between. So, let us say it is a 10 round, this is basically the first one, this is basically 2 to 9, and this is basically the 10th one, but that has to be counted. So, it is possible you can implement this using one state, but then you have to put a counter where you are counting how many times I entered. But whatever it is, no matter which algorithm you look at, the core part of it is finite state machine, and therefore, attacks on finite state machine needs to be considered. Now, data path could have problems. So, for example, the laser fault injection or just normal fault injection, even the data path, if you have a value of 0, 1, 1, if any of them flips, that is also a problem. We need to look at that vulnerability, but finite state machine, the specific one we are going to look at, that depends on what threat model you use. Here we are using these 3 threats or 3 kind of things we call as vulnerable, and this work actually got integrated in Synopsys Spyglass, which is worldwide everybody uses to just check their designs. So, do not care states, do not care transitions, and the laser fault injection vulnerability. So, what is the key idea? Basic idea is, if you have drawn a finite state machine like this one, do you have states hanging here and there that nobody knows? Those are the unspecified ones, nobody knows about it and nobody tested it. An attacker is likely going to sit there and then do laser fault, whatever it is. So, the first question I am going to ask you, why on earth these 3 states are there? I did not write it my VHDL Verilog code, you did not write it, then where did it came from? I am looking for few hands, those of you write VHDL Verilog code or synthesize. Where did this state came from? Just do the little counting with me please, 1, 2, 3, 4, 5. How many extra are there? 3, 5 plus 3, does that give you a clue? 2 to the power 3 is 8. So, in your mind, my mind, when I wrote the code, I had 5 case. I did not put the default, or I do not care, right, even if I did not care. But because there are 5 states, whether the synthesis tool do binary encoding, one hot encoding, it really does not matter. It needs to use 3 bits, a state register it need to use, that register needs to have 3 bits, and I can assign some values. I can assign 0 0 0 here, 0 0 1 here. Of course, that encoding is important, it is not random, but I am just making it random, 0 1 0 0 1 1, and then this one is, let us say 1 0 0. But the other 3 also would be named in some way, 1 0 1 1 1 0 1 1 1. So, the amount of do not care states you have, that is the vulnerability you kept it for attacker to attack different ways. So, it is not a good idea there, it is not even a good coding style in any good company's coding book. You have to have a default statement, you have to have encoding for those. So, that is about that is actually easier to solve. So, how do you mitigate this problem? Just add a default state, add more states, they may not have anything, just maybe print something saying why are you here, right. Trespassers will be prosecuted or something you print, then you know that state should, nobody should have gone to that state in the first place. Register should not have assigned that value under any circumstances. But the bigger problem is the next one, do not care transitions. If you have 8 state, how many possible transitions are there? N square, right, n square possibility. So, 64 possible transitions, no matter how you count, let us count together 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, total 10 transitions you are going to verify. Remaining 54 transitions nobody is going to verify, nobody is going to check, and those transitions are going to happen due to laser fault injection. Can anybody help me, how would it happen in laser fault injection? I did not do the state encoding right, just to illustrate. I should have, whom did I give 0 0 0? I did not give anybody? Wait key, what did I, it looks like, oh I wanted to write 0 0, okay, that is 0 0 0. Now, if I flip just the leftmost bit, I already reached the final round. Through laser fault injection I talked earlier, I reached the final round. So, and if my laser fault injection capability is 1 bit, that is good enough for me to do that. And so, but remember that transition does not exist, but we never check that transition. If that transition happens, what to do, we do not have any assertion. So, therefore, that attack is possible, that is why that is a vulnerability. So, this do not care states, mitigating that vulnerability is easy, adding another 54 transitions, I do not think anybody will like that idea. No designer in right mind will accept that area overhead and all that stuff, but nonetheless that is a similar stuff for this. I will zoom in later more, but laser fault injection vulnerability, computing those vulnerabilities. So, how do we compute these vulnerabilities in the first place? So, do not care states is as simple as number of unspecified states over all number of states. How do I compute? If you have b bits of encoding, 2 to the power b is your total number of states, out of that how many states you have, and then total. In the previous example we have 8 possible states, 5 was basically specified over 8, 3 over 8 is what the probability, this probability is. So, for do not care transitions, this is little complicated for a reason, it is not important, but what is important is this do not care state, if you look at it from a layman terms, if you have b bits, total number of states are 2 to the power b, total number of transitions are n square. So, that minus how many transitions you already have divided by 2 to the power b square. That extra complexity is there are transitions, there are state machines in cryptographic library where you cannot have 2 to the power 2b transitions, because number of inputs that drives that finite state machine is not going to have those many states and those many transitions. So, that is why if n is the possible inputs to the finite state machine, if it is less than b, then it is a slightly smaller bound than that, but either way it is still a very large number. This vulnerability is huge, and there is not much you can do, at least by adding more transitions. The laser fault injection vulnerability I will zoom in more, but the question is how many states are vulnerable, and then over the total number of states, this I will talk about.
So, one
Yes,
question here. So, you mentioned that the Synopsys spyglass has those checkers, right? So, what it exactly checks there?
So, Synopsys spyglass actually is kind of checks a lot of stuff. It is like a software analogy of linting tool. it checks memory buffer overflow and all that stuff. So, they did not have any security checking. So, this is one of the first one they introduced, but that is a $1 billion product, or they are one of the second or third biggest component after design compiler. That is what they sell. At the RTL level, people just run the spyglass and gives all kind of the clock tree violation and all that stuff very early, so that people go and do the layout, and then they figure out, oh, I have this parasitic effect. And so, as much as possible they pushed it up in the RTL level, and so that they can check all those scenarios, different kind of path and delay.
So it's basically check how many states are unspecified in your FSMs.
It's more like a warning message, and designer may look at and say, hey, I do not care. It's more like it analyzes, and designer will say, okay, I understand, I do not care, that kind of stuff.
So
but this one, the solution is also implemented. I will zoom into the LFI.
So threat model is like in the downstream somewhere somebody use those don't care state to implant some.
They will use those unspecified states. They will make a sitting on there, and then or maybe install a Trojan there, which will stay there as it is, and with laser fault injection or otherwise they will make the transition to another state. So, basically hiding in the unspecified functionality. So, LFI will talk later. So, I did not spend more time. So, information leakage in the security community, two areas is going to stay for a long time. One is side chain analysis. Many people think they are same, they could be different. Information leakage and side chain analysis, or those areas are going to stay active. The chances of the hardware Trojan and puff and the logic locking is likely to go away, because funding has kind of dried out those areas. So, that is the indication. So, information leakage, as the name suggests, if you have a design, where you have a secret S, which of course secret S will travel. It is a design, it is connected somehow, but there may be a if statement here, if privilege then do something, right. But if somebody can mount an attack on that variable P, then and make this true even when it is in user mode, then that data can transfer. That is why in the information leakage analysis community, there are two ways of looking at it. One is statistical analysis. Can I compute the probabilities? If you recall earlier, we talked about if you have an AND gate and the probability of both input is 0.1, then output has a 0.25 probability of being 1. So, if you can propagate that way, you compute a probability of, first you have to identify what are your shared values. In case of cryptographic library, it is basically the key, wherever is the key variable or any other variable which can directly imply the key variable, you create a set of that, and then from that set you kind of propagate this static way of probability calculation all the way to the output, and it is quite likely all variables will propagate to the all outputs, but the probability values would be very low. Then that tool would give that whole listing of the leaky paths, and odds are all the millions of paths would be listed, nobody would be interested, probably the top 10 path would be listed. Designer looks at it and say, yeah, that is fine, that has a privilege, that would be fine. In fact, this idea of leaky path computation or information leakage, it is not just for hardware cryptographic library, even for software cryptographic library. One of the well known concept or compiling cryptographic library, Dr. Karfa is world leader in that area, has been the secure compilation. In the basic idea of secure compilation is the following, and we are talking about secure compilation for cryptographic libraries only. So, secure compilation idea is following. If you have, let us say, a C program, think of your cryptographic program, cryptographic library program, let us say AES, and when you compile it and get the binary, this compiler job is to ensure the performance is good, the area requirement is less, power dissipation is less, but suddenly we are imposing for cryptographic library that it should not create binary which is vulnerable. How do you define vulnerable? Let me use the information leakage example. On the C, I compute the information leakage function and find the leaky paths, or let us say just take one path, topmost path. What is the probability of that path? Let us say 0.25, or find n number of paths. The definition of security in this domain has been, after compilation, the number of leaky paths should not be more than of number of leaky paths in the original code. Ideally, you do not want to have any leaky path here for a cryptographic library. Ideally, that should be the objective. But the point I am trying to say is, even for software cryptographic library, when you compile, when you compute the leaky path, remember if privilege statement will be there, key will travel through the design. That is, otherwise if key does not travel, how the computation happen, all these XOR and encryption, how does it happen? But you want it to be happening in a specific mode. And in fact, many interesting situations, security engine maintains the key. When security engine through that bus requests the AES to do the computation, it has to transfer the key through the, it has to transfer the key through this path. So, it is not the key is staying stored inside the AES, that would have been ideal. If you can protect the AES, you are done. So, key will travel through the bus, and that causes this leaky problem. But as I said, in software domain things could be different, but ideally you want to create a situation binary has no leak, no leaky path. But as you realize, when you have a code, when you have anything, it would leak. So again, if you are interested in doing, you may want to do PhD with Dr. Karfa on this area. Any question? Yes, please.
One query, sir. Previously you had explained us about the homomorphic encryption. So like you have suggested that the security enclave that key transfers to the AES, can homomorphic encryption be used there?
So, if you do homomorphic encryption, you do not need AES, right? You do not need AES, but remember, homomorphic encryption solves the problem of computing with encrypted data, right. But when you are doing the encryption, homomorphic encryption does not do that. So, you are using AES, key is traveling. So, all these problems still remains. You are going to use your AES software library, AES hardware library, those will remain. In the computing frame, you do not need trusted execution environment, that is all it is. Any other questions? So, the information leakage, all I wanted to highlight, information leakage problem is an interesting problem in software domain, hardware domain. How people exploit this leaky path, that is different. Software domain it would be different, hardware domain it would be different. For example, if the information does not leak, then some of these side channel attacks will not be possible. In the microarchitectural attack that I talked earlier, cache timing attack, the value gets transferred to the cache, right. It should not have propagated that time. In here, based on a side channel, you are kind of, so it is a leak, but it is not the leak I just talked few minutes ago, the leaky path. It is not actually coming to primary output. We do not care about primary output. We are trying to find how much power you consume, and by looking at the power footprint, we are trying to figure out which computations you are doing. That is the information leakage, but not the one I discussed. So, you are still finding some information about the computation, right. And of course, this is a simple power analysis. These days people use more sophisticated ones, because attacker knows you are going to do this. So, they will try to hide. So, then there are sophisticated one, differential power analysis, higher order differential power analysis, and so on. Now, if you want to do at the program level, at the software level, this would also work at the RTL level analysis. There are at different level you have different types of analysis, and there are information flow tracking techniques. So, static one I talked about, you compute the probability in your design starting from the secure path all the way to the output, you compute the probabilities of each of the gate. If it is a gate level, that is a static one. In the dynamic one, you can instrument with the tagging. So, for example, if B in that domain, this is called tainted, although technically it is not be tainted, somebody is secure, it should be respected, right. but in the community they have somehow called them tainted. If B is tainted and if there is an assignment like this, C would be tainted too. So, that is why this tagging information happens. This is known as explicit information flow. Implicit information flow would be here C is equal to B, which is fine, but there is also another component, and this component part, because it is a this assignment is part of a if statement. So, that means information about A is also percolated here. So, that is why if A is true or B is true, C is going to be true. So, this is kind of implicit information flow. Any questions on difference of explicit versus implicit? Explicit is if B was 1, C will be 1, and if anybody is printing C or have the ability to view C, they know about B, that is obvious, that is the explicit. Here it is implied because it is not direct here, but because it is inside the if statement, this would not have been executed if A was not true. So, if this got executed, then you know for sure A is true. If A is your secret variable, then and if you print a print on C and let us say C was initialized to 0 by the attacker, if C comes to be 1, then you know C was modified. If that is the only place it modified, not here, it was made 0 here, then you know for a fact A was true. May or may not be, because B could be true also. Either way, it would not enter if A was not true. So, then you know the secret information of A is percolated to variable C. Now, technically this is correct, but this is conservative. Let me illustrate. If you have an AND gate, so information flow says any function, if input has taint, output will have taint. And if I apply that argument, if I have A and B and output is C, it should give me a function that C is always the taint propagation, if I use C underscore taint, A underscore taint or B underscore taint. I am not saying it is wrong, but it is not conservative. More precise answer would be. So, these are all these are imprecise, implicit imprecise, explicit imprecise. Why it is not 1? Because we know for AND gate who is the dominating input, 1. If any of them is 1 and we are interested in B, B is my secure variable, it actually propagates. But B if A happens to be 0, B actually does not propagate to C. So, this should be a precise information flow tracking. If you do the probability, do the computation correctly, then you have to do a model, different truth table. There are all these problems have been solved by Mohit Tiwari from UT Austin. So, basically then who will flow, that precisely defined at gate level, there are researchers who defined it at RTL level. There is a lot of work in this area. Any question on precise versus imprecise and implicit versus explicit? Precise basically means we do not go by the conservative definition that output is always tainted if any of the inputs are tainted. Now, we are making an exception if the controlling variable is not my security gadget, then that variable does not contribute, that does not propagate. Oh, controlling variable is not security gadget and it is set to controlling value, which is 0. OR gate if it is set to 1, then does not matter what is the other variable, output does not get reflected on that. Any questions? So, if you simulate it, if you simulate any of these design, tag it, and all you observe, let us say in this particular example C is a primary output variable. If you get certain value or change in the primary variable, then you know value got propagated during simulation. It is not a guarantee. So, that is why what formal verification people do, they basically figure out always A, which one is variable, let us say B underscore T not equal to C underscore T. So, they basically check this property that does not matter how many possible paths are there, these two tags should never be same, they should not track each other. You can write different way, b underscore t implies not a underscore t or vice versa. Then that would give you a formal guarantee. You still need to do the tagging, either you do simulation, simulation does not guarantee, simulation only says the time you simulated information did not flow. But if you can check it, then you can guarantee that that travel indeed did not happen, will never happen. Now, I am going to talk about information flow in different other I chose one or two cryptographic algorithm, elliptic curve, the encryption one, this is the encryption standard, and this has different modules, start, multiply, and in that order. So, if you are trying to see through side channel, you are going to, so remember in side channel a couple of important points. One is finding the boundary, which component is where. Second thing is getting rid of noise through different kind of differential analysis, and so therefore, doing the timing right, putting the right boundary, that is one of the key kind of area or work. And once you do that, and also another thing is, unless we apply correct input, information may not flow, because remember in information flow tracking or a shared variable, for it to go there you have to set certain variable right to increase your probability. Remember the AND gate, if you had an AND gate and the secret value you want to pass, the controlling value is set to 0 for some reason, then it is not going to work. You have to make sure that value to the controllability, if you remember, you need to find input that would set that controlling value to 1. So, that if there is anything in the secured transfer path, that can flow through. So, therefore, important test generation is also important. You cannot just simply do side chain analysis, you plug in something, get something, it is not going to work. So, you have to get traces where a specific computation being done will produce a significant difference in the something getting computed, something not getting computed shows you a difference. If everything looks same, you will not be able to distinguish them. If somebody is multiplying with the 10 versus multiplying with 20, you want to differentiate it. So, once you have that, and then typical different stages of computation, it could be static power, simple power analysis or differential power analysis, then you kind of check, can I distinguish it? If I can distinguish it, if I can find it, if I can figure out the key, then basically I am successful. And of course, there are these errors of false positive and false negative, and you want to kind of handle all of those, and there are mechanism to kind of, if you partition it right, then that problem can be addressed. And when you partition, so I just wanted to show you something, when you partition in different ways, too fine or too high, this type 1 error and type 2 error is kind of has a interesting characteristics. If you have too many partition, then your type 2 error is going to go down. Let me just double check, type 2 is false negative and type 1 is false positive. And if your partition is kind of less, then your type 1 error is kind of down. So, therefore, you want to find a area, this marked with yellow here, you want to find a area where you want to perform your experiments where both of these errors are in kind of controllable range. And here are some stuff, but the thing I want to talk about, although I did not introduce these ideas earlier, I will briefly talk about shuffling. You already know, AES already has a shuffling operation there. Blinding, as the name suggests, blinding is a mechanism of, think of you are encrypting, you want to give some data to somebody, but you do not want that person to understand it. So, typical one of the way to do is kind of blinding would be just you kind of encrypt and give the data, but it is similar to homomorphic encryption, you have to rely that such a computation actually exists where they will return the data to you. But even if you do any of these stuff, the blinding, of course, without mitigation the attack is very successful. Even with some types of mitigation, for example, blinding and what is this 2, one of these scenario or one of the run, it actually it was broken. So, so blinding, simple blinding did not work, suppling and blinding or just suppling, global suppling, that all worked for Montgomery multiplication, which is part of the ECC code. One of the function of that multiplication is part of it. So, you want to really analyze module by module and all that to figure out which one is, and the way you kind of do different double addition and all that Montgomery, what you want to basically figure out. So, minimum alpha value, which is basically this color, this green color, any stuff that going below this color, that basically means you can statistically guarantee that you can figure out those values, and in this particular case just happens to be these red ones. So, Montgomery multiplication is just fine, and so normal multiplication, these blue lines will just go below here. If you use just normal multiplication, that is actually a mitigation on elliptic curve cryptography. We kind of extended this idea to a domain that I want to introduce to you. It is called cryptographic instruction set extension. Now, the motivation for this one is the following. So, software cryptographic algorithms, you have all these reconfigurability that makes it pleasant, but in hardware cryptographic algorithm everything is like kind of rigid and tight, but hardware is fast, right? It somehow feels like more reliable. Software is kind of flexible, but it is not really fast, not most power efficient, and somehow gives a feeling it is probably not the most secure one. So, that is why the RISC-V community came up with this idea of cryptographic instruction set extension, where you basically have a set of instruction set and some modules to kind of combine the advantages of software cryptographic library and hardware cryptographic module. Let me just do this animation to see if it works. So, think of a cryptographic algorithm, it does not matter what algorithm it is. This I could be AES, this could be elliptic curve cryptography, one could be RSA, it is just two cryptographic algorithm, has some sub computations. Remember, many of them invoke SHA, you can think of SHA as one of the invocation, and if you look at the common color, if I did it right. So, this color is common, this function is called at different stages. Why am I getting same color, maybe different color, this color is same, this color is same. So, basically these components are same. So, what RISC-V community did, they analyzed all these cryptographic libraries and figured out what sub function is same, and they designed an instruction set for that. Let me see if I have the so that basically means, remember, add, subtract, multiply, divide, all these are kind of granular computation. Somebody somewhere in the world figured out that no matter what program you run, bubble sort, insertion sort, searching, whatever you do, this add, subtract, multiply would be needed. That is why they created those modules, that is why instructions are created. Same analogy RISC-V community did, that if you look at AES, let us not implement whole monolithic AES, look at sub functions of it and implement them, such that those sub functions can be used. If somebody wanted to implement ECIES, they can implement it. So, that means let us think of AES, and let us say AES would involve by using this analogy CR1, it does not matter what it is, CR1 and CR3. Maybe ECC will use CR1 and CR2, maybe few more. So, the key idea is those are the instruction, corresponding modules are over So, corresponding modules are these, similar analogy to add, subtract, those are common functionality between different programs. Think of cryptographic modules also as program, these are the common elements on those programs, and corresponding instructions has been made. So, we looked at this problem and we thought, well, nobody did any security verification on them, why not us? So, then we basically looked at and analyzed them. There are a lot of interesting problems and challenges. eraser is disabled. So, there are many interesting problems and challenges, but basically flow is pretty much the same as any other flow. Here only additional thing is, for each component we are kind of evaluating them once, are they vulnerable, then each component we are evaluating on the whole system. And why, I will give you an analogy why we are doing this without using cryptography name, I will give you the analogy. So, for example, when you design a processor, right, you have a processor and then you have a memory. Let us start with the memory. Let us say you designed a memory, you tried testing it all possible ways, but you observed for some of the negative numbers, -5, -15, -35 is failing. Still you wanted to take a risk, put it in the system is working just fine. Nobody found that problem ever. Can anybody tell me why?
Probability of using those numbers.
One is probability, the processor, the way it is generating addresses, it is all 2 to the power I and none of these numbers are 2 to the power I. So, it will never generate, that is one way. And if these are the addresses, none of the load instruction, all these addresses will be positive. Now, ideally when you verify the memory, you should have knew these constraints, you should not be trying to verify for everything and anything, but I am just simply saying when you put on the system, sure it opens some bugs, but it actually hides many more. Some of the bugs were previously not visible, it kind of makes those paths kind of easy to view, observable, but more often than not, it actually hides many scenarios, because although this primary input, it has all 0.5 probability and all that, very uniform, nice and fair story, but as it goes through the stages, the inputs and lines, everything imposes lot of constraint, and deeper this module in the design, what it comes to itself is kind of restricted. So, therefore, if you just do analysis and here and say, oh, it is vulnerable, but in real world that vulnerability or that power propagation, that information propagation could be suppressed. So, that is why it is an important kind of to look at that. So, there is a lot more details than that for obvious reason, but what I wanted to show you.
One question.
Yes, please.
So, what is those CR1, CR2 if you try to relate them with say AES?
So, one of them that is actually not correct, one of them you can think of SA.
So, one instruction for the entire SA.
But actually SA is also divided. I just wanted to say ECC also uses SA, then one more program also uses SA. So, whatever the subcomponents everybody uses, that is basically the thing.
So, this is publicly available also?
This is all it is like RISC-V, everything is publicly available for everybody. And you can
its implementation also available, very low.
All implementations are available for all RISC-V, instruction set extension, anybody did any analysis, anybody identified any problems, everything is publicly available. So, now as expected when we run on the AES, so there are two kind of variation of cryptographic extension that is available in the public. One is its name is crypto, another's name is X crypto. So, we looked at two modules in them, one is AES mix, you asked me what are those CR1, CR2, it is AES mix and it is a AES sub, right. So, it is really the mixing functionality and subtract functionality, and as you can see the expected power and the observed power is exactly matches. So, you can exactly figure out what is going on by doing simply the power analysis. And many of these implementation did not use many of the mitigation technique, they being open source and the first time, eventually they will do. When you run, you will probably not observe such a beautiful scenario, but once you kind of, so same thing for SHA.
Hello, I have one question.
Yes, please.
So, this instructions may not be a real 32-bit instructions kind of thing, input data particularly.
Yes.
It may not be 2, 3, maybe more number of data may be needed. So, you require separate different kind of interface for this kind of instructions maybe some ROCC extension kind of thing.
You are talking about this instruction
This
set
instructions,
extension, right?
yeah, particularly
No,
CR1, CRN,
so
maybe not small instruction, maybe bigger instructions.
Right. So, these are already defined, this could be modified, I do not think it is a gold standard,
Yeah.
but the exactly the way add, subtract, multiply, the instruction set for RISC-V has been defined. Can we change it? Sure, we can propose if there is a reason, but these are also defined. So, by looking at all the functions of all the cryptographic and what are the common few instruction or 5-10 instruction, they define those code.
No, but for decoding and sending data for that,
Oh, that has been incorporated in the decoder of RISC-V.
yeah.
That, so it is not the original RISC-V. The RISC-V that support cryptographic instruction set extension, the X crypto and the crypto one, they have that additional logic that will distinguish these instructions.
Okay, okay. So, this
So
is
basically-
actually, we cannot say it is a instruction set extension from RISC, but it is actually separate cryptographic processor having a different set of.
RISC-V has at least 2 if not 3 instruction set manual, one for original one which does not have any of those, another for the people who are interested in operating system kernel level programming, that is a privileged one. Unlike most processor where everything in the same manual, they have 3 different manual, and the third one will have the just the cryptographic extension. Right. So, for AES also it is completely full recovery of data. For SHA also same 2 modules crypto and X crypto, SHA 256 and SHA 512, it is the full recovery. Now, we also wanted to look at that if we kind of use different type of mitigation like the operation blinding or some affine masking and all that stuff, if you want to do that, so then what happens to the thing. So, this affine one seems to be kind of passing, that means the attack is not successful, but the blinding, we saw that blinding story earlier, the blinding actually fails the leak down test, that means we will be able to figure out the values or whatever, or key whatever you are trying to figure out.
What is this p value and CPA and DPA, what is that?
So, this is this one is differential power analysis, this one is correlation power analysis, thank you, correlation power, and the p value is the p value obtained, and I am guessing when it says fail it is below the p value of what is assumed to be statistical probability, below which you know that.
So, here affine masking means you marks those instruction and check, or what is that?
I need to double check, but this is the mitigation of masking, and
this is your work, right, or your group work?
Our work, yes, yes. Affine masking is, I think this affine masking actually this solution exists, we just applied that on the instructions.
The TVL is exactly the same the way you do TVL for AES, or
So, there is a little bit of difference, and some of those differences are basically one is test generation of course, then victim identification, then boundary, and fourth is doing on the unit level and then on the system level. So, there are just few those minor differences, otherwise it is TVLA. So, this is basically a logical point, and we can take a break, or I do not know, 15-20 minutes, half an hour, I am not sure. How many of you have energy to continue, or you want to take a break and come?
Take a short break, 15 minutes.
Okay, sounds good.
Okay, so we'll take short break and come back after 15. So it's now 3:33, 3:45 will come back.
Good afternoon. Now, we are going to talk about different mitigation methods. In the last lecture, we kind of looked at different types of vulnerabilities in cryptographic libraries, and now we are going to look at how do we mitigate some of these vulnerabilities. And here is a laundry list. I will go slowly and zoom into one of them. So, I will zoom into this particular one of identifying vulnerable states and transition, but other one I will just quickly go through. So, when you talk about power level vulnerability, some form of masking is usual, and any time in security domain you masking, and Nilatpala is a leader on this area. So, anytime you talk about masking, then if you have a variable x, you want to mask it with something. Typically XOR is a very efficient area and performance efficient operation. If you mask with any key or any other variable, then whoever is looking at it does not get an idea about the variable x, and the recipient or when its absolute original value would be read, XOR has a duality property. You XOR it again with the same value, you get back the original value. Timing protection. Timing protection, if you kind of look at, let me illustrate that problem first for the timing protection. So, in elliptic curve cryptography, if you zoom in Montgomery and few other places, there are codes such as if key bit I equal to 1, then you do certain stuff, else you do certain stuff. Now, if you have a code like this, an attacker knows about it, then during the profiling of power, what is going to happen? You are going to see certain computation of certain type will be happening, and then little bit of time something else. You will be able to find a difference, and from that you will figure out where it is taking a long time, that is probably the if part, and where is a short time. So, this is the if part, this is the else part, the time, because here are the 4 instructions that will take longer to execute versus here are the 2 instructions. You still have to find the boundary where it starts, all that you have to do, but once you do that, this timing mismatch in the if and else, that is the vulnerability somebody will exploit to kind of figure out. Once you know this, you know more than something, then you know this bit is 1, this bit is 0 of the key bit, you already figured that out. Now, whether it is 1 1 or there are 2 1, that is kind of sometimes confusing, but whatever it is, because this computation is based on key value, that is a direct attack. Sometimes attack is not direct, timing imbalance, you figure out something, using that you figure out something, using that then you find the key bit, right, exactly the way Dr. Karfa talked about the AES attack, multi-layer one after another after another. Now, can anybody tell me what is the mitigation of such a vulnerability? If you have a code in your program of this nature, how do you mitigate it? Balancing, the balancing. So, basically if there were 4 instruction here and 2 instruction here, you add 2 more instruction here. So, balance it out, so that its kind of time is same. Same analogy happens even when any power side channel attack. This is the timing one. When power side channel attack, when people kind of look at something taking a long power, then less, then long, and then less, people can figure out, well, what operation is going on. How do we mitigate this story? Some operation is taking more, some operation is taking less. How do you mitigate? Of course, you would want the one which is taking less to compute such a way it takes less power, that would be ideal. Most of the time that is not possible. Whoever is taking less, you pull it up, you basically pull it up and make it take more. You pull it up and make it take more by adding lot of garbage instruction. It is not a good idea from power dissipation or area perspective, but that is basically the mitigation. So, that you kind of make a nice profile, but as you know, this simple power analysis attack will not work, but once you do correlation power attack or differential power analysis attack, then basically you might be able to still figure it out. So, that was the timing protection. Then fault injection by modular redundancy and multiplication. This one we already talked about, the rare nodes and branches. We talked about that can you reduce the rareness of the design and then kind of do the check. And leaky paths we talked about, if we can compute leaky paths and designer get to know about it, then designer will try to see how do I stop, pause or add some stuff to kind of make sure those leaky paths does not exist anymore, right. So, let me now zoom in and spend little time to kind of show the FSM state vulnerability elimination, that basically solution is kind of integrated in Synopsys tool. Before I go there, for software modules, so the previous ones are applicable for software as well as hardware. Many of the software modules, the kind of some of the techniques that either exist or we proposed or somebody proposed, as you can see there is not a laundry list of items, it is mostly blinding and kind of temporal duplication. And so, in this particular case blinding is something different, it is not kind of XOR. If you recall, for RSA, the encryption, when we are trying to do encryption of a message, we are basically trying to do, we are taking the message, we are doing the public key of where we are trying to send modulo the n, that is what we are trying to do. All you have to do extra here, you add for blinding, you add a random variable. So, first of all it has to be a random number between 1 and n, and it has to be relatively prime to n, just to not violate any of the characteristics of RSA algorithm. Then, and if I implement that in software, this is exactly how it would look. You are just basically trying to do this R, you are basically going to introduce there, right. And by using their existing library and functions, it is actually simple 1 or 2 line of code addition, that would be your mitigation for the software. And remember, you have that Witchy proof test. So, once you do the mitigation, now you run the Witchy proof test to see if you still have the vulnerability or blinding actually took care of it. Any questions? So, let me now go back to the state machine and kind of zoom in how this vulnerability mitigation happen. I am taking an example of a doorknob, but basically most of the cryptographic libraries has the finite state machines, and those finite state machine has the encoding, either you explicitly stated the encoding or after synthesis encoding happened, and those encoding will have values, those states will have values. And then problem is when you have those values, and if you kind of want to unlock the door, so from the door locked state, all you have to do flip just this particular bit to 1, and that would let you get in. We talked about it, and the reason it works. So, the kind of analysis we want to do on any kind of security algorithm is that we want to divide the all possible states in different categories, and typically these are the kind of 3 categories we consider. The one in the green is kind of anybody, it is a non protected states, and then the ones that through password check or whatever can go to some of the protected states. So, this is basically unprotected, this is basically outsider, unprotected, non protected, whatever that is. These we do not care, they are outsider. This one kind of authorize some people who are allowed to access the, and of course, these are the protected states, all these are protected states where you are changing the state or doing something important. These are protected state, and this dashboard which is somewhere in the middle, that is kind of authorization or authorized state. So, typically when you have a set of states, you want to divide them in certain classes based on your design. And why you are making this distinction? Because these states under no circumstances should lead to those red states, that is basically the idea. They should always go through authorization states, password check or whatever it is. So, that is what you want to check. And we talked about this hardware implementation earlier, where you said that all these state machines are implemented using a register. In the previous example, If you can just flip the first bit to 1, then we actually got the access. So, question is how do we, so what is our objective then? Let me go back and see if my capability, let me even go back farther, one more step farther. If this is my design, by changing one bit I can go to the unlock state just by changing one bit. What is my solution then? My solution depends on what is my laser capability. If laser capability is 1 bit, I want to make sure there is no state here in the unprotected state that can go in the 1 bit change to any of these, ideally the unlock state, right, or write password or unlock state. How do I achieve this? Let us focus on this sleep one, let us ignore. How do I achieve this? Yes, please.
Increasing the Hamming distance.
Increasing the Hamming distance. Right now Hamming distance is 1. If the capability is 1, I want to increase the Hamming distance to at least 2. If these are the only 2 states, if I could have made it 101, then that would have worked. Even if it can flip any of the 1 bits, it will still not match with the encoding of the protected one. So, the question is how do we find, and remember that finite state machine will have lot of states, how do we encode, how many bits are needed, how do you compute? We looked at basically couple of solution. So, exhaustive is of course interesting, you try all possible combinations and try to choose the encoding which is cheapest, a small number of bits. There is a work on probabilistic encoding. So, there are also work on somebody figured out the codes and there is a table lookup database, you can look it up. Given the number of states, given the Hamming distance if you are looking for, if you give them number of states and the Hamming distance, if you provide these 2 pieces of information, then they will give you the code. So, it is a huge code base, it may not fit for you, but then there is another one that probabilistically tries to figure out, and very quickly you will see it actually mathematically it is supposed to work, but real life it does not work. It took us some time. First of all, the dissertation was written in German, it took us some time to understand it, and then we kind of figured out. I will share that with you. Now, going back to the same, so the algorithm for this one, if somebody told me that the attack capability is 1 bit flip, which is Hamming distance of 2, and there are n equal to 5 state, right. So, then we basically start with 3, if n equal to 5 we have to start with 3, right, you cannot start with 2, and if we start with 3, if we start 0 0 0, that is the first one, no problem, you keep it, and then if it is 0 0 1, this is not going to work. So, then has to be dropped. If it is 0 1 0, distance of 1 is not going to work. So, we really want distance of true, so that we can put in. So, this story kind of continues, we keep or we let it go, and some point 1 1 will not work and we are out with all the 3 bit encoding, but I have to cover 5 states. So, now I have to go for the 3 is exhausted, I have to go for the 4, and again in the 4 we can start with certain number and either we keep or we drop, and this story continues. In this particular case, this might be the answer. So, this is basically the key idea what we are trying to do, very simple idea, simple heuristic, and so by going back to that example, we basically exactly what we said 1001. So, then none of these unprotected states by 1 bit flip you will not be able to go there. So, basically what is the efficient way to find that state encoding, and this problem could be complicated. We kind of looked at that there could be a finite state machine which has a child finite state machine which would be a different kind of register encoding. How do you solve those problem, dependent and independent and hierarchical and all that. Now, in terms of kind of the results, as I said, the probabilistic one was kind of very interesting work, and as you will see it does not do well, but later we realize this probabilistic one actually do better when Hamming distance is really large, it does amazingly well. But for the finite state machine encoding, the Hamming distance the Hamming distance or the laser fault capability is really small, 1 or 2, maybe in the future 3 or 4. So, probabilistic actually does not do well for that. When you have a Hamming distance of huge, you are doing lot of mathematical computation where you need a code word, probabilistic does amazingly well. So, this is basically the kind of result that if you do probabilistic for a very small, so ledger fault capability of 1 bit flip, then with increasing number of states the probabilistic one really go high, but for a small number exhaustive and our approach is kind of fine, but as the number of bit flip capability goes up, then exhaustive is, as expected, exhaustive is going to do worse, because you are trying all possible combination. Probabilistic still does not do well, and this simple heuristic will do well. It is not optimal. So, there is a lot of scope for improvement, and in terms of even number of kind of looking at the encoding length, how many bits we needed given different number of states with different amount of bit flipping capability or ledger fault power. If you kind of look at it, the probabilistic one actually do pretty bad because it is a small number of capability, but our results kind of closely matches with what exhaustive will find in terms of number of bits. It is just that exhaustive takes a long time to find it. Now, in terms of area overhead, when we kind of look, all of these techniques were applied on it, they were developed for cryptographic algorithms only. Really we are kind of looking at for these examples, as you can see, the protected states and non-protected states on different types of design is actually not that much. It all depends on the algorithm, and then so the grouping is a kind of a another layer of advantage, which basically the key idea of grouping that we looked at. Without grouping basically means every state we kind of think of independent, and they should not travel from one to another. That is a very stricter condition. Instead, the grouping method said if you have 3 types of group, which is basically just think about the protected state, let us say this is think about a non-protected state or maybe the authorized state. What we are saying is we actually do not care if a state here is trying to make a transition here, who cares? They are nobody anyway to start with. So, if anybody tries a ledger fault injection tries to go between them, we do not care. What we really care, I mean most importantly is the following: nobody from here should come to here, that we definitely care. As long as Hamming distance from any of the code word here is more than the flipping capability plus 1 distance away from here. Oh no, other way around, non-protected state to protected states. As long as that distance is, that Hamming distance is more than bit flipping capability plus 1, then we are kind of do. That is the grouping approach. So, as a result the grouping approach sometimes will do little better, but many cases it really did not do much. But the thing is area overhead is not that much, because in addition to state encoding or case the number, you have so much of code in there. I believe that is pretty much all I had, and thank you for today. See you tomorrow at 10 o'clock.
Okay, so again ahead of time today.